Hello, everyone. Good afternoon, good morning, good evening. And I'm Yishang Wang from the National Taiwan University. And today we are thrilled to have Professor Arthur Gretton to give our lecture on probability divergences and generative models. Arthur, let me just give a very brief introduction of Professor Arthur Gretton. He is now a professor with the Gatsby Computational Neuroscience Unit and director of the Center for Computational Statistics and Machine Learning at University of College London, UCL. He received degrees in physics and systems engineering from the Australian National University, ANU, and a PhD with Microsoft Research and the Signal Processing and Communications Lab at the University of Cambridge. So he previously worked at the Max Planck Institute for Biological Cybernetics and at the Machine Learning Department in Carnegie Mellon University. So Arthur's research interest in machine learning includes the design and training of generative models, both implicit, for example, GANs, and explicit, for example, exponential family and energy-based models. Other interests include non-parametric hypothesis testing, survival analysis, causality, and kernel methods. And if you have heard of MMD, maximum mean discrepancy, Arthur was the key person who proposed MMD about 15 years ago. Okay, so without further ado, let me introduce Professor Arthur Gretton with a virtual applause. And let's all welcome Professor Arthur Gretton for the next 3 hours lectures. Arthur, you can take the lead.
So thank you very much for the kind introduction and for the invitation to participate in the MLSS. I only wish I could be there in person, so hopefully before too long I'll be able to travel again. So the topic is probability divergences and generative models. I should say as well that I like lectures that are interactive, so I have my chat window open. So please, if anything is not clear, don't hesitate to ask questions. I'm also going to pause at appropriate times to take questions from the audience. So it's not the lecture is not a race. I want everyone to understand, and so I'm very happy to take questions. Okay, so I'm going to have basically two themes in this lecture, or two problem settings that I'm going to care about. The first is training generative models with divergences. So first of all, what is it that I mean when I talk about a generative model? Let's say that I have a collection of samples from a distribution P. In this example on this slide, this is a collection of photographs of bedrooms, okay? And now I want to train an algorithm that is going to generate samples that have a distribution that matches that of P. So I want an algorithm which is going to generate additional pictures of bedrooms. And this set of new fake bedrooms is going to match the distribution of my original set of real bedrooms, okay? So this is not, the goal here is not to just draw one very, very good picture of a bedroom. It's to draw many, many pictures of a bedroom that sort of cover the space of plausible bedrooms, all right? And to train this algorithm, I need some notion of a cost function. But this cost function should compare distribution. So it should compare like the set of real bedrooms to the set of fake bedrooms, and to tell me how far apart the distribution of fake bedrooms and real bedrooms are. And then I can use that as a cost function, right? So I can use that to bring my real bedrooms and my fake, or I can use that to train my algorithm to bring the fake bedrooms closer to the real bedroom. So my cost function I'm expressing on the bottom of the slide here is dpq. This is a divergence measure between P, the distribution of real bedrooms, and Q, distribution of fake bedrooms. And that's going to be my loss function. Although, as we're going to see in this talk, maybe it can be a little more than just a loss function, but that's for later in the talk. Okay, here is another setting that I care about, which is not using a divergence to train a model, but to use a divergence to troubleshoot. Okay, so let's say that I have a set of samples from a distribution P, and in this case, P is CFAR 10. And let's say that I've trained my learning algorithm on P. I'm very confident it's doing well. It's classifying dogs from cats and so on. And now let's say that I've got a new distribution of samples, CFAR 10.1, and I want to deploy my model on this new distribution of samples. So that's Q. A question that I might be concerned with is, are P and Q the same? Is my distribution that I trained on the same as the distribution I'm testing on? Or in fact, do I have some distribution shifts? So do I have some shift in distributions that means that maybe my algorithm that I learned on P is not going to do so well on Q? So in this case, I can use the divergence as a test, as a measure of whether the difference between P and Q is sufficiently large to be important. And I'll talk about what I mean by important. And if it is, then I might start to worry. I might think, well, if I trained on P, I'm testing on Q, maybe I'm not going to do so well. Okay, so this is a second setting in which divergence is very important, because it's going to tell me how far apart P and Q are. Okay, so these are two problem settings. And now this is going to lead me to the outline of my talk. So there are many different types of divergence. And this talk is going to discuss two sort of broad families of divergence. The first are the integral probability metrics. So MMD is one of them, and Wasserstein's a very famous one. The second are the phi divergences, or F divergences. And interestingly, what we're going to see is that when phi divergences are used in machine learning, they're in fact used in a way that's a little bit unexpected, and which actually makes them, in many senses, closer to IPMs than to the original F divergences. And arguably, this is why phi divergences, as used in machine learning, work as well as they do. So that's, I think, a provocative argument, but I'm going to make that argument in this talk. Okay, so once I've introduced divergences, then we're going to start to use them. Okay, now the first example in which we can use divergences is to train a generative model. All right. Now we can use divergences to train a GAN. So I think everyone attending the summer school has heard of GANs. And you can use a divergence as a critic function to tell my generator, my algorithm generating samples, how to make its samples closer to the target. So GANs are very well known. But what we're going to see is that we can actually include the critic function into the sample generating process. And this is quite new work. This has only happened in the last couple of years. And we can show that this is always going to perform better than using a generator on its own. Okay. And then finally, we're going to talk about this troubleshooting problem. Right? We're going to talk about how to compare samples with MMD, maybe, to detect when, like, let's say our test sample is different from our training sample, and we need to worry about distribution shift. Okay, so this is the outline. And I'm going to sort of pause at natural places. I'm not going to sort of talk solidly for 3 hours. And those pauses are going to be used to have some questions and give everyone a break. Okay, so let's start with divergence measures. Okay, I have two distributions, P and Q. I want to compare them. Broadly speaking, at a very high level, what kinds of things might I do? So on the left-hand side here in the green circle is one thing I might do, which is I might take, in some sense, a difference, P minus Q. Yes, of course. So the question is, can students have a copy of the slides? Definitely they can. I'm going to make the slides available for download very shortly after this talk, so everyone can get a copy. Yeah. Okay. So I want to compare distributions P and Q. There are two ways at a very high level that I can go about it. One is to take the difference, P minus Q. Okay, in some sense, I haven't yet defined. And if this difference, P minus Q, is 0, then I conclude that P and Q are the same. Okay. Another approach I might take at a very high level is to take, in some sense, a ratio of P to Q, okay, P divided by Q. And if this ratio is everywhere 1, then P and Q are the same. So difference or ratio. This is, at a high level, two ways of comparing distributions and being able to conclude when they're the same or not. So the integral probability metrics live on the left-hand side of this plot. So they fundamentally are based on a difference in probabilities. The phi divergences live on the right-hand side of the plot. So they are based fundamentally on a ratio of probabilities. So let's drill down a little bit. how do we actually witness this difference in probabilities? How do we detect that P minus Q is 0? The way that we do that is we look for G, a function, in some class of suitable functions, so in a class of well-behaved functions in a way which we haven't yet been explicit about, which maximizes the difference in expectation. So I'm going to look for a witness function from a class of functions that maximizes the difference in expectations under P and Q. And if all of the functions that I use in my witness function class result in a difference of EP of G minus EQ of G being 0, then I can be confident that P and Q are the same, like as long as I've got enough functions in my calligraphic H class. All right. So these are the integral probability. Yes, good question. What's in the intersection? I'm coming to that. Let's now speak about. Okay, yes, indeed. So first of all, I'll talk about the phi divergences, and then I'm going to answer the two questions that we just had. Okay. So the phi divergences are the expectation of some function of the ratio of P to Q. Okay, this function has to be convex. It has to be. It has to return 1 when the ratio is 0. Okay, ratio of densities is 0, and it has to be lower semi-continuous, which is a property I won't talk about too much. Okay, so basically, what I'm doing, I'm taking the expectation of a convex function of the ratio of P to Q, where this function is 0 when the ratio is 1. P and Q have to have densities for this to be defined. And moreover, this ratio has to be defined. So let's say that P has support, P has mass, where Q doesn't. Well, then I'm in trouble because then I got to divide by 0 and everything breaks. So one has to be, I think, a lot more careful about defining phi divergences in IPMs, just because I need to make sure that my probabilities have densities and that this ratio is well defined. Okay, so we had a couple of very, very good questions that just came up. One is, what's in the intersection? So you'll notice that there is an intersection, and this is not a typo. There is only one trivial divergence measure that is both an IPM and a phi divergence, and that's the L1 distance, okay? The total variation distance between P and Q. So it's the integral of the absolute value of P minus Q. That is the only non-trivial probability metric that is both an IPM and a phi divergence. Nothing else lives there. Okay, so in particular, I've got my integral probability metrics like Wasserstein or MMD. I've got my phi divergences, which are like KL or Jensen-Shannon or chi-squared. I can never write a phi divergence as an integral probability metric unless it's total variation. Likewise, I can never write an IPM like MMD as a phi divergence. Okay, so KL has no integral probability metric form. MMD has no phi divergence form. So indeed, this point that there is, let's say, a fundamental difference between these two classes of divergence is the case. And that's something I want to really emphasize in this slide. So I hope that answers the questions in the chat. These are very good questions. Okay. Now let's spend a little bit of time in the integral probability metric side. So the reason I'm spending time on this side first is that, in my opinion, this side is actually the easiest side to understand. So I'll spend some time here first. Let's first of all think about the Wasserstein distance. I won't spend too much time on that because there is other people who are much better at that than I am. I've given some references on the bottom of the slide. So there's entire tutorials and summer school lectures on the Wasserstein distance. And so I urge you, if you're interested in using it, to look at those as long as the lecture that I'm about to give, and that will help you to understand Wasserstein. So I'm just going to give a very short introduction here. Remember the principle of the integral probability metric. I'm looking for a well-behaved function that maximizes the difference in expectation under P and Q. Okay, now what do I mean by well-behaved in the case of Wasserstein? Well, these are the functions whose Lipschitz norm are bounded by 1, which is to say that if I take f of x minus f of y divided by the distance x minus y, and I do that for every possible x and y, this ratio should be less than or equal to 1. Okay, so you can sort of see. So I'll return to phi divergences shortly. So if you're patient with me, I'm going to come back to those, answering Lauren's questions. So yeah, So basically, here we have an example of the f function that maximizes the difference in expectation for a simple toy example, where I've got my blue points and my red points, okay? And you can see that the slope of this function is bounded by 1, which is enforced by this constraint here. And as I move my red towards my blue, we can see that Wasserstein goes down. So here it's 0.88, here it's 0.65, so it's decreasing. Now, this means that my critic is helpful. What do I mean by helpful? Helpful means that as my red approaches my blue, so let's say as my fake bedrooms approach my real bedrooms, the Wasserstein distance is going to decrease. So I have a cost function which is telling me that I'm getting closer to my target. Now I'm going to show that in cartoon form by a helpful professor here. So this is my helpful professor who is giving me constructive feedback on what I'm doing, is telling me that I'm getting closer to the answer. And Wasserstein distance has this property. It has the nice property that when Q converges weakly to P, the Wasserstein distance goes to 0. And this is a property that we're able to take advantage of where we're using it to train generative models. Okay. So that's the Wasserstein distance. As I say, like that's all I'm going to say about Wasserstein distance, but it's important to describe it because it's one of the classic integral probability metrics. But please see these references below for much more detail on that divergence. Okay. Now let's look at the maximum mean discrepancy. So the difference between MMD and Wasserstein is I've chosen a different class of well-behaved functions. In this case, I've chosen as my well-behaved functions the unit ball in a reproducing kernel Hilbert space. So what on earth does that mean? Let's find out. All right. This means that I've chosen as my class of functions a function that is a linear combination of a particular feature dictionary. Okay, so this is my function evaluated at x. This is expressed as the dot product of the coefficients f, f1, f2, f3, and on, with a dictionary of features of x, phi1, phi2, phi3, and so on and so on. All right. And I've got a unit ball constraint here, f less than or equal to 1, which amounts to saying that the sum of the squared f's has to be less than or equal to 1. Okay, so that sort of tells me, in a sense, like how big my function's allowed to be. Okay, so I've taken these functions, I've multiplied them by these very carefully chosen feature dictionaries, and this gives me then my function here. So one thing I want to already emphasize very much about the feature dictionaries is that as I go down the list, the feature dictionaries get less and less smooth, okay? But they also get smaller and smaller in amplitude. So what that means is that as I take a sum of these features that get less and less smooth with smaller and smaller amplitude, I'm going to end up with a smooth function, a well-behaved function. Okay, so the idea is not so much to map the blue dots, and I'm just answering Tom's question here. It's not that we map the blue dots and the red dots to the line. What we do is we take the expectation of the green line under blue, the expectation of the green line under red, and then we take the difference in these expectations. And I'm trying to find a function that pulls apart these expectations as much as possible. Okay, so why employ Wasserstein distance? It's a very helpful distance when I'm training a generative model. And the reason is because as I get my red points closer to my blue points, my Wasserstein distance is decreasing. So it's a fantastic cost function if my algorithm is creating red points and I want my red distribution to match my blue distribution. So Wasserstein distance has that property. And as we're going to see, MMD also has that property. So that's why, Wasserstein distance has been used to train a GAN. It's called the Wasserstein GAN. And this motivates using Wasserstein to train that. So Martin Najowski and El Botu have written a great deal about that. Okay, so let's go back to MMD. So I've said that I have a smooth function which maximizes the difference in expectations under P and Q. Okay, and this this class of smooth functions is a sum of features, right? So I've taken a weighted sum of features such that the sum of the squared weights is less than or equal to 1. And I've argued at a high level that this is going to get me a smooth function because the features become less smooth as I go down the dictionary, but decrease in amplitude. All right. So I've written my function as a sum of infinitely many features. I have an infinite feature dictionary. And infinity is a very big number, and it's hard to represent on a computer. So how is it that I can, in practice, compute my function here? Okay, because it seems at first sight to be impossible. I need to solve for infinitely many features. So the trick is that I've chosen my feature dictionary in a very particular way, such that I know the dot product in closed form. Okay, so here's my feature dictionary. This notation here just means that the sum of the squared features is finite. So that means that my features have to be shrinking in amplitude as I go up the dictionary, as I've argued on the previous slide. And it so happens that if I choose my feature dictionary correctly, I can compute the dot product between these features in closed form without explicitly representing my features. And so if my algorithm to compute f only uses dot products, then I only need to express the dot products. I never have to express the feature dictionary explicitly. Okay. So how do we define a well-behaved function? This would actually be a lecture on its own. At a high level, two things need to apply. One is that the function class needs to be rich enough that I can distinguish any difference between P and Q. The second is that it has to be smooth enough that when I compute EPF minus EQF, I don't just get infinity every time. So it has to not be so wiggly that I just get infinity, whatever my P and Q sample, but it needs to be rich enough that if there is a difference between P and Q, I'll spot it. This is a very delicate balance to make. To describe how to choose the MMD to achieve that balance would be a lecture on its own. So I urge you to look at my webpage for more details on that. For the expense for MMD, I'm going to come back to that later. Yeah, but in short, the cost for computing MMD is square in the number of samples. Okay, so here is my MMD. I've said that it's a sum of infinitely many features. And I've said that if I can compute the dot product between these features, then I never need to write down this entire infinite feature dictionary. Okay. The example of the feature dictionary that I gave in the previous slide is a feature dictionary corresponding to a very particular kernel, which is the exponentiated quadratic kernel or the Gaussian kernel. Okay. So these feature dictionaries that I gave on the previous slide, I can take their dot product in closed form, and the closed form dot product of these features looks like a Gaussian. And I emphasize that when I compute the MMD, if the MMD is a function of these features, and if I can compute my f using only kernels, which I'm going to show very soon that you can, then I never need to write down this infinite feature dictionary explicitly. Okay. Now, there's a very good question about other divergence measures. So a famous divergence measure is the Kolmogorov-Smirnov distance. This is actually an integral probability metric as well. This actually, just to explain to the audience, the Kolmogorov-Smirnov distance looks for the largest difference in the cumulative distribution functions of P and Q. Okay, and if this largest distance isn't too big, then I can conclude that P and Q are close, and if it's 0, I can conclude that P and Q are the same. Now, Kolmogorov-Smirnov works great in one dimension, and to get it to work in more than one dimension becomes extremely difficult, extremely fast. So Peter Bickel has done some work in that direction, and you can have a look at his papers, and you'll see why it is that people don't use it in more than one dimension after you've looked at his papers. Okay. Whereas MMD and Wasserstein are actually quite a bit easier to compute in more than one dimension. Okay. So here is my maximum mean discrepancy. I'm looking for a smooth function that maximizes the difference in expectations under P and Q. Now, I've talked about a well-behaved function class. The well-behaved function classes for MMD are called characteristic RKHSs. So these are reproducing Kono-Hilbert spaces that are rich enough to detect any difference in P and Q. But they're also smooth enough that when you compute it on samples, you're not just getting infinity every time. Okay. So characteristic RKHS have this property. For the purposes of this talk, all you need to remember is that the exponentiated quadratic kernel has that property. So that's a rich enough RKHS such that it can detect any difference in P and Q. Okay. For those who are familiar with the energy distance of Shekeli and Rizzo, this is also an MMD, and you can define the kernel for that. We have a paper in Annals of Statistics describing why the energy distance is an MMD. So for those who care about this or who know about this, I'm just going to give you that citation. Okay. Now, I've claimed that I can compute the MMD, or I can compute this function using only dot products, okay, between features. So I never have to write down my infinite feature dictionary. And that's a strong and very important claim, because if this distance between P and Q is going to be practical in any way, I need to compute this function. Otherwise, it's just like a mathematical game. It doesn't have any purpose, okay? So I'm going to show you how to compute this function using a particular trick, which I'm describing in this red box here, which is, core to this definition of MMD is the expectation under P of a function f, okay, and an expectation Q of a function f. Now, the trick is that the expectation under P of this function f is the dot product of the coefficients that define f and the expected features. The expected features under P, okay? Now, in finite dimensions, that's always true, and it's trivial. It's just a very simple statement. In infinite dimensions, one has to be a little bit careful in taking the expectation inside the dot product. But if my kernel is bounded, I'm allowed to do it. And I won't say more about this here, but it's just for mathematicians among you, we can be confident that this is allowed, okay? So that means the expectation under P of f is the dot product of the coefficients that define f and the expected features under P. Now, this is going to be the core trick that we're going to use to be able to compute f using only kernel functions without this infinite feature dictionary. So let's see now how that works. Okay, here is my MMD. Expectation of PF, expectation QF. F is in the unit bowl in an RKHS. In this case, an RKHS corresponding to the exponentiated quadratic kernel. Now, this green function is the smooth function for this little toy example here where I've got my blue points and my red points. Okay, and that's the function that maximizes the difference in expectation. So clearly I've computed it here, so it must be computable. Okay, now I'm going to use the trick that I described on the previous slide. Okay, expectation under P of f is the dot product of the coefficients that define f and the expected features of P. Okay, now here is my coefficients that define f. Here's my expected features under P, expected features under Q. Okay, so that term here is from this term here is from that, right? So now I've got an interesting problem to solve. I need to maximize the f, whose norm is bounded by 1, dot producted with mu p minus mu q. What might be the f that maximizes this dot product? Right? Here it is shown geometrically. Here is mu p minus mu q, is this vector here. Here is f confined to its unit bowl, and I want the f that maximizes the dot product with this vector. So what is the f that does that? Well, is it this one? Well, no, clearly not either of these, right? It's in fact the unit vector, which is pointing in the direction mu p minus mu q. So this is a vector that maximizes the dot product with this mu p minus mu q vector of expected features, or difference of expected features. So we're now at the end of the proof. We substitute this in. Then we notice that the dot product of this with the unit vector in the same direction is just the norm. So what we've shown is that the MMD is just the norm in feature space of the difference in feature means under P and Q. So MMD is the difference in expected features under P and Q. Okay, this is a very particular property of MMD and no other IPM. Okay, so this happens because I'm using a Hilbert space, a space with a dot product, as my space of well-behaved functions. If I use a Banach space, like I did with the Wasserstein distance, which doesn't have a dot product, I can't do this trick. Okay, so I've shown that the MMD, the integral probability metric, is the norm of the difference of expected features under P and Q. Okay. If there's questions, by the way, I'm still monitoring the chat, so feel free to ask if anything is unclear. All right, using this trick now allows me to compute my function using only kernels. All right, so let's show how I've computed my witness function. I'm going to first of all say what it is that I do to compute it, and then I'm going to tell you why that's the right answer. Okay, let's start with what yes. Yeah, it's the reason I put this f less than or equal to 1 is because then I'm optimizing over a convex set, whereas like on the unit ball there's a non-convex set. As it so happens, the supremum is attained when f hits the boundary, so it's kind of like an academic question in this case. But this is sort of to make the set over which I'm maximizing convex, which is helpful to me. Okay. So let's say that I want to compute my witness function, my function that detects the difference in P and Q. How do I do that? So here are my samples from P, x1 through xn from P. Here are my samples from Q, y1 through yn from Q. Now, what does my witness function look like? Well, let's say I'm using an exponentiated quadratic kernel, so a Gaussian kernel. Okay, I put little Gaussian bumps on my blue points and little red Gaussian bumps on my red points. Then I add all of the blue bumps together to get a blue curve. I add all the red bumps together to get a red curve. I subtract the red bumps from the blue bumps, and that is the witness function. Done. Okay, that was very easy. No infinite features, etc. Okay, now why is it correct though? Okay, remember from 2 slides ago, I said that the optimum of my witness function is, after some constant of proportionality, the difference of feature means under P and Q. Okay, so that's my coefficients that define my witness function. Now let's say that I've got samples from P. My empirical feature mean is just the empirical average of my features of my P points, right? So I've got these xi's drawn from P. I take the empirical average, and that gives me my empirical feature mean. All right. Now let's say that I want to evaluate my witness function computed on these empirical means at a point V. Okay, so V is just the point along this axis here, B. Yeah. Okay, I want to evaluate my witness function at a point B, but I don't want to have to write down the infinitely many features of V or this infinitely long feature mean. All right. Now, I know that this is, up to some constant of proportionality, the difference in empirical feature means dot producted with V. But now we have a trick, right? Because we know in closed form the dot product of phi of xi and phi of V is just the kernel between xi and V. Yep, I will read questions out loud. We're not saying them in future. Good point. Yep. Okay. Yep. Okay. So dot product of empirical means of P minus empirical mean of Q. Well, empirical mean of P is this expression here. The dot product of this individual phi of xi with phi of V is the kernel between xi and V. We know that in closed form. Okay. So here is our function. The sum of the kernels of xi and V, so these are the little blue bumps, minus the sum of the kernels between yi and V, so these are the little red bumps. So I've never needed, when I'm computing this function, to write down my infinite feature dictionary. Okay, I can compute this function using only dot products between features. So this is, I think, a tremendously powerful and useful thing. I don't even have to solve an optimization problem. I've just got this. As soon as I've got my samples and I know what my dot product is, my kernel is, I can compute my witness and I'm done. So this is an exceptionally easy integral probability metric to compute. And so this is, all of those witness functions that I plotted before, this is how I got them. Okay. Now, is the maximum mean discrepancy a helpful critic function? Well, let's think a little bit about that. Okay, so here is my maximum mean discrepancy. Okay. And for the particular, let's say, kernel that I've used here, which is an exponentially quadratic kernel, I would argue that this is a helpful critic, right? That here MMD is 1.8, here MMD is 1.1. So evidently, as my red points approach my blue points, so as my, let's say, generated points approach my, let's say, training sample, we can see that the MMD is decreasing. And that's great, right? Because I'm giving helpful feedback to my generator. My generator generating these red points is improving because it's pulling its red points towards the blue target. So it's a constructive generator. And in fact, for the exponentially quadratic kernel, we can show that MMD metrizes weak convergence. So if red converges weakly to blue, then MMD is going to go to 0. So apparently, MMD is a helpful critic function. Or is it? Okay. Now, what happens if I use an exponentiated quadratic kernel, which is very narrow? Okay, same kernel, but a much narrower kernel. If I use a much narrower kernel, I get a much bumpier function. And you can see that this function, departs only very locally from 0 around the red and blue points. And in particular, as I move my red towards my blue, MMD is going down by such an infinitesimal amount that it's not really giving me useful feedback. So I'm using an exponentially quadratic kernel. So in principle, it's a characteristic kernel. As red approaches blue, MMD should go to 0. However, it drops so slowly for this kernel that I can't detect it to numerical precision. So I'm expressing this as this angry teacher here who just yells no at you, whatever you do, unless you get the perfect answer. It's not giving constructive feedback to my poor student here who's trying to generate points that approach my target. Okay, so depending on the kernel that I choose, I might have a helpful critic or I might have an unhelpful critic. So if my goal is to, let's say, improve my red points and push them towards my blue, if my goal is to use the MMD as a cost function to train a generator. All right. So that's, do we have any questions about integral probability metrics before I go on to phi divergences? I'm just looking at the chat now. So it's unhelpful in the sense that, let's say that I have MMD as a cost function, right? And I'm using it as a cost function to train a generator, which is placing red points. Now, if I improve, if my red approaches my blue, I would love for my cost to decrease. Because if my cost were to decrease, then that sort of shows me that I'm on the right track. Now, in this example here, the cost actually does decrease, right? It goes from 1.8 to 1.1. That's great. It tells me that as I move my red towards my blue, I'm doing better. Okay, so this is a helpful teacher that's giving constructive feedback. If I use a kernel that is too narrow for my problem, I'm moving my red towards my blue, but the MMD is decreasing by such a tiny amount that I can barely detect it. So let's say that I'm trying to extract some gradient signal from the MMD so I can push my generated red points towards my blue points. Well, evidently that's not happening here because MMD is decreasing by too small an amount for my generator to realize that it's improving as it moves its red towards the blue. Does that help? So if my only goal is to say is red and blue different, then fine. This tells me red and blue are different because MMD is not 0. But if my goal is the next step along, which is to optimize my red towards my blue, well, that's not being done here, right? This is not great. Are there any other questions before I go on? Okay, so where would one use an IPM versus phi divergence? That's a very good question that I think I'm going to be able to answer once I've described, let's say, what people are doing in practice when they say they're using phi divergences in machine learning. And what we're going to see is that when we use phi divergences in practice in machine learning, we might be doing something closer to an IPM than to a phi divergence. Yeah, so why doesn't the restriction of the norm of M guarantee helpful critic, right? That's a very good question. Let's say we've got this, this is a question that's a little bit subtle, so I'm going to go back a couple of slides and describe what's going on, okay? when I choose my exponentiated quadratic kernel, I choose a bandwidth. When the bandwidth is very narrow, what happens is that my feature dictionary decays slower. Okay, so basically, like my less smooth features, or how to say it. Okay, let me say this another way. When my kernel is very narrow, this smoothness constraint here is less, let's say, restrictive. And so basically the functions that I'm getting out are going to be less smooth than they would be if my kernel is very broad. Basically, as I use a narrow kernel, I'm getting, like, let's say, more wiggly features here. And if I get more wiggly features, that means I get a more wiggly function. That's the clearest way I can explain it in this lecture without a lot of additional slides. Is it always good to choose an exponentiated quadratic kernel? So exponentiated quadratic kernel is characteristic. So in that sense, it's always good at detecting differences in P and Q. However, it may be that let's say different kernels are helpful for different problems. Towards the end of the lecture, we're going to be looking at kernels defined on neural net features, for example. And these are going to be much more useful for detecting differences in distributions over images. Okay. Next question is, can MMD be negative? To answer that question, I urge you to look at this equation here, right? MMD is the norm of the difference in feature means. Is the norm ever a negative? No, right? The length of a vector can only be either positive or zero if the vector is zero length. But I can't have a vector of negative length, right? So the MMD cannot be negative. All right, great. I'm very happy to have questions, by the way. So this is, I enjoy interactive lectures, so keep them coming. Okay. Phi divergences. Let's spend some time on this side now, okay? Unit consistency of MMD. I'm not sure I understand that question. Could you type a little more? Okay. Anyway, I'm not sure I understand that question. Let's talk about the phi divergences, and then this is going to be able to answer the question that arose earlier about whether one should use phi divergences or integral probability metrics in practice. Okay, oh yeah, what units does MMD have? So one cannot really talk about MMD as having units. What one can talk about is whether MMD is significantly different to zero or not. So that's something we can talk about. MMD can be defined as a metric as long as my function class is rich enough, right? So a metric is zero only when distributions agree, right? That's one of the properties of the metric. So if I use a rich enough function class, then indeed it's a metric. Now, let's say that I use a much more impoverished function class. Let's say that I use a function class which doesn't have too many features in its dictionary. In that case, there might exist P and Q where MMD is zero, even though P and Q are different. In that case, it's not a metric anymore because a metric is zero only when P and Q are the same. So it's a metric as long as I have a rich enough feature dictionary. Okay, so now let's spend some time on the phi divergences. Okay, so phi divergences contain a lot of divergences that everyone knows and loves, like KL, chi-squared, Hellinger, reverse KL, Jensen-Shannon, and so on. And remember how we've defined a phi divergence. It's the expectation under Q of some function phi of a ratio of P to Q. Okay, and so this ratio has to be well defined. So I can't be in a situation, for example, where P has support very broadly, and Q has support that's very constrained, because then I'd have a ratio of something on zero, which is a problem. So this ratio needs to be well defined. Phi, remember, has to return zero when the ratio is one, because when the ratio is one, P and Q are the same. And phi also needs to be convex. I need a convex function here. Okay, why are P and Q metrics called phi divergences? You would have to ask the history books that, I don't know. But they have a phi in their definition, so that might be a clue. They're also called F divergences, and when they're called F divergences, the phi is replaced by an F. So for overfitting, this is not really a question that I can answer. So let's perhaps continue. And like if MMD is 0, would that lead to overfitting? That's it depends what one means. Like that, the question sort of depends a little bit on the application that one's considering. So that's, I think, my answer for that question. Okay. Why must phi be convex? We're going to see that very soon. Okay. So here are the phi divergences, okay? Expectation under Q of the phi of the ratio of P to Q. Phi has to be convex, we're going to see why shortly. Low is semi-continuous, and phi of 1 is 0, okay? Now, the classic example, which I'm going to spend a lot of time on in this talk, is the KL divergence. So the KL divergence is like your favorite phi divergence that everyone learns about in undergrad. And so I'm going to really like focus all of my attention on KL. Okay, now KL has the phi function u log u. Okay, so this is actually a strongly convex function. It's a very well-behaved function. And when I substitute u log u into the definition of the phi divergence, what I see is that I get these q's here, q and q, canceling, and then I get the expectation under P of log P on Q, which is the good old KL divergence. All right. So this is the KL divergence. Let's say that I want to use the KL divergence as a critic function to train a generative model. Is that a good idea? Maybe not, right? So let's say that P and Q have disjoint support. So that means that the ratio is not defined. So P has a density which is only non-zero on this interval, and Q has a density which is only non-zero on that interval. All right. Now, this is a problem because the KL between P and Q is infinite. And it's infinite even as I move my red towards my blue. It's just infinity all the time. So this is as unhelpful a critic as possible, right? This critic just tells me, no, whatever I do, wherever I place my red points, unless my red points overlap my blue points perfectly. Okay, now you might argue, well, this is just really bad luck, right? I've got this strange situation where my red and my blue points don't have overlapping support, but in real life, the ratio is always well defined. Well, that's actually, Jovsky and Botu argue very convincingly against that. If you're generating, let's say, images in very high dimension, like you do with the GAN, then your support of your GAN image distribution and of your real images is never going to overlap in such a way that you get the ratio well defined, right? So you're always in this situation where your critic is this angry teacher that's yelling no every time. Okay, this is the typical situation. This is not the abnormal situation. So this is a very strong argument that the phi divergences are a terrible idea for training GANs. And same with Jensen-Shannon. What's Jensen-Shannon? Well, it's log 2, like it's not changing, it's not decreasing. So Jensen-Shannon is again a very bad idea for training GANs. But that's odd, right? Because there's 10,000 GAN papers that say otherwise, that are all using either Jensen-Shannon or KL or some other notion of phi divergence. So clearly something's working, but we've just argued that it's impossible. So what on earth might be happening here? Okay, to describe what's going to happen, I need to give you this one slide of theory, and then I'm going to describe what people really do when they say they're using phi divergences for training GANs or for other things, okay? And what we're going to see is that when we see what people really do, we will see that the divergence measure that they use actually does behave well in this scenario. Okay. Okay, how often does the disjoint support happen in practice? And there are examples here. If the distribution is a Gaussian, or if there's a normalizing flow with a Gaussian base measure, then this is not a problem. So this is absolutely right. Like if I had, let's say P and Q were two Gaussians, the ratio would be well defined. Okay, and then I could compute the KL. And I've even got that example later in the talk. However, if I'm using this divergence to train a GAN, okay, the image space is very high dimensional. The support of plausible image in this super high dimensional pixel space is a very low dimensional submanifold. Now, the images that I generate using my generator are also on a very low dimensional submanifold. And it's very, very likely that these submanifolds are not so perfectly aligned that the ratio of densities is well defined. In fact, it's certain that this is the case. This argument is made in this paper here. This is not my argument. So in the event that we're generating samples in very high dimension in a low dimensional submanifold, as for example, images, this is what's going to happen. We can guarantee that this is what's going to happen. So is it a common situation in practice? Well, yes, it is. Yeah. Okay, so once I give this slide of math, then I'm going to describe what people are doing in practice when they use phi divergences to train a GAN. Okay, but please bear with this one slide of math first, because it's going to introduce a tool that I'm going to use in the next slide. Okay, I'm going to introduce a new representation of phi, my convex function defining my phi divergence, which is a slope-intercept form of that function. It's called the conjugate or Fenchel dual of that function. So what is this slope-intercept form? I'm going to say, well, I'm going to give you a slope, okay? Then I'm going to take the tangent line at that slope. So V is my slope. I'm going to take the tangent line at that slope. And phi star returns the negative of the intercept. Okay, so phi, this dual function, I give it a slope, it gives me the negative intercept of the tangent line at that slope. And this slope-intercept form of phi, if phi is strongly convex, that's unique, right? Because if I give myself a slope, well, there's only one tangent line that has that slope. And that tangent line has a unique intercept for this strongly convex function. All right, so this slope-intercept form of phi is an equivalent form of phi. It's the dual form. All right. Is everyone clear about this slope-intercept representation of my phi? Okay, I give it a slope, take the tangent line at that slope, get the negative intercept, that's the dual. Okay, and that's an equivalent representation to my original function. Now, what if I take the dual of the dual? Interestingly, and here convexity comes to our rescue, we get right back our original function again. If I take the dual of the dual, I get back phi. Okay, and so phi now I optimize over the slope, and x is the point at which I evaluate. Now, why have I done all of this? Well, I've now expressed phi of x as an optimization, as a solution of an optimization problem at every x. Okay, so what I need to do if I want to compute phi at x, I need to solve this optimization problem in terms of this phi star function, in terms of this dual. So you might say, well, I can just compute phi of x straight away. I don't have to solve an optimization problem. But it turns out that expressing phi as a solution of an optimization problem is going to be very useful in the next slide. Before I go to the next slide, are there any questions? Okay, so I've expressed phi as a solution of an optimization problem, which uses this dual representation. You can convince yourself of this property at home. It's just a couple of lines. It's very easy proof. Okay. Now, what do these functions look like for the KL divergence? Well, we already know phi of x is x log x for KL, and you can compute phi star in closed form. Again, it's just a couple of lines. It's very easy, and it's e to the v minus 1. So that's the form of phi star that I would use if I was expressing phi for the KL divergence as a solution of an optimization problem. Okay. So if I substitute this phi star here, then I get back the KL when I solve this optimization problem at every x. Or I get the phi for my KL, I should say, when I solve this optimization problem at every x. All right, this is my slide of theory. Now let's use it. Okay, here is my phi divergences again. Okay, phi divergence of p to q is expectation under q of phi of the ratio of p to q dz. I'm just doing this for a generic phi right now. Next, remember that I can express my phi at P and Q evaluated at Z as the solution of an optimization problem. So for every single value of Z, I need to independently solve, I need to independently solve this optimization problem here, right? I find this FZ that maximizes PZ, QZ, FC minus V star FC, okay? And if I solve this problem for every Z, then I recover my phi, okay? So right now I've just written this line here as an equivalent form, but I haven't actually done anything yet, okay? Now what happens if I don't solve this optimization problem perfectly? Let me bring back the chat window. What happens when I don't solve this optimization problem perfectly? What if instead of solving it perfectly for every Z, I use a smooth function instead, which isn't able to perfectly track the solution of this optimization problem, but tries to come close, okay? Subject to being smooth, subject to being well-behaved, right? If I do that, then I have a lower bound, right? I haven't solved this optimization problem perfectly, so I must get a lower bound on my original phi divergence, okay? And this lower bound is what we might use in practice if we're using a phi divergence to solve problems. Okay, so I'm only, the question is, what if P and Q are sign measures? I'm only concerned in this talk when P and Q are probability measures. So that means that they're non-negative and their mass is 1. If they're sign measures, that's a whole different talk. Yeah, okay. Now, I've expressed this, I've lower bounded this as a solution of an optimization problem for some well-behaved class of functions. When is this lower bound tight, right? Well, it's tight when F diamond is in the class calligraphic H, where F diamond is the derivative of phi evaluated at the ratio of P to Q. So if my function is rich enough that it contains within it the derivative of phi evaluated at this ratio, then my bound becomes tight, okay? If my function class isn't rich enough to contain this derivative of phi evaluated at that ratio, then whoops, my bound isn't tight. I've got a lower bound. Okay, how are X and Y defined? So X is sampled from P and Y is sampled from Q. So I'm using color coding here. I should have explained that. So basically blue is P, red is Q, okay? So this is the condition under which this bound is tight. But if I use a smooth function class, well, maybe F diamond's not in it, right? Okay, so this is a lower bound on the phi divergence. Let's see what that looks like in the case of the KL. All right, so here's my KL, expectation of the P log ratio P to Q. Here is the lower bound, which uses the phi. Remember the phi star. Now remember, we've defined the phi star a couple of slides ago. So I've upper bounded KL by sup over F of minus E PF plus 1. So I basically reparameterized my problem to use minus F plus 1 as my function class. The reason for that is that it's going to make the slides a lot clearer later on. So please be patient with that little quirk. So I've got, sup over F minus E to the minus PF plus 1 minus EQ E to the minus F, okay? This is the variational lower bound on KL, okay? Where I've used a smooth function. When is this bound tight? Remember from the previous slide, I've said that the bound is tight when F contains F diamond, which is the derivative of phi evaluated at the ratio P to Q, okay? Now, in this case, F diamond has to be the negative log ratio of P to Q. So if the negative log ratio of P to Q is in my class of well-behaved functions, then this bound is tight. Let's look at an example. So I promised you earlier on that I would talk about the case of Gaussians. Here I'm keeping my promise. So here I've got a red Gaussian and a blue Gaussian. They've got the same variance, they've got different means. What is the negative log ratio of P to Q? Well, it's a straight line, okay? So if the straight lines are in my class of well-behaved functions, then I can make that bound tight for this particular example where I've got two Gaussians with different means. Yeah, okay. So so this is my lower bound in the case of the KL. Now the question here, is F underscore Z a constant or a function? F underscore Z is a function. for every value of z, I need to solve for a different fz. So as I change z, fz is changing. So fz is absolutely a function of z. And here I'm expressing f as a smoother function. Now, remember fz is the ratio of p and q evaluated at z. So it's like d phi p on q at z. I hope that makes it clearer. Is this related to the elbow? No, it's not actually. So the elbow is a quite different lower bound. Yeah. Now, would the optimization problem here mean trying to make the bound tight? Now, that's a very good question. Maybe we don't want a tight bound. Okay, I'm going to come to that shortly. Maybe we want a loose bound. Maybe a loose bound is better. That's a very astute question, and we're going to see, in fact, later on, that a tight bound might not be a good idea. Okay, so here is my KL. Here is my lower bound on the KL, which becomes tight when f is equal to the log negative ratio p to q, if this ratio is defined. Okay. Now let's say instead of a population p, I've got samples from p. So xi are drawn from p iid, yi drawn from q. Okay. Now that means that I replace my population expectation with an empirical mean. I replace my population expectation with an empirical mean. All right. And this is a problem I can solve. Okay. So subject to choosing a good function class here, I've just got a difference in means I can solve. Like if I've got a neural net class, if I've got a kernel class, I can solve this problem. Okay. So I'm going to call this a KL approximate lower bound estimator. So this is going to be the KL divergence. So the KL divergence sounds like the KL divergence, but it's actually quite different. And these variational lower bounds are what people use in practice when they use a phi divergence as a critic for training generative models. So you can also find a lower bound for Jensen-Shannon, for reverse KL, for chi-squared, and so on and so on. All of these lower bounds are in this beautiful paper here, which everyone should read. The original idea of using this lower bound was proposed in this paper here. Okay, so we've got our KL divergence, which is not the KL. Okay. Can we always switch the expectations with respect to Q and the supremum operator? So I don't think I've ever switched I haven't taken supremum inside the expectation here. I've just solved it. Yeah. Okay. So let's say that we're going to compute in this nice example, the KL, the variational lower bound on the KL, using a reproducing kernel Hilbert space as our function class. All right. The equations to do that are in this archive report, which is online. So if you want to see what I did to compute these functions, please look at this report and you'll see all the expressions for them. But I'm not going to derive them here. Okay. So I'm looking for a function in a reproducing kernel Hilbert space that maximizes the difference under the difference of expectations under P of f minus eq e to the minus f plus 1. Okay, f is in an RKHS, and I'm applying this smoothness penalty to f, just as I did for MMD. Okay, so if I'm penalizing the norm, like let's say bounding the norm by 1, or saying that the norm should be small, that amounts to getting a smooth function out. Okay. So this is a lower bound. It's, because of this constraint, it's not going to be a tight lower bound, but it's going to be a lower bound on the KL. And it's going to be a lower bound because I've enforced that f is smooth. So we're going to call this the KL smoothie. Okay, let's look at that example for the toy problem that I introduced earlier, where I've got my red points and my red points here, my blue points here, and I'm computing my KL, my lower bound on KL, for this case. Okay. Two things to notice. First of all, it's not infinite, right? My original function, my upper bound is infinity, okay? But the KL, the lower bound, is not infinite. It's 0.18. And for this choice of function class, as my red approaches my blue, the KL, this lower bound, is actually dropping, okay? So this is really a very helpful property of KL, which is not true of my original KL. Okay, which is that it's a helpful critic function. As red approaches blue, this KL is decreasing, right? And it's well defined even though red and blue have disjoint support. So there is no density ratio here. Density ratio is not defined. But I forced this function to be smooth. So my KL is not infinity, right? The KL is, but the variational lower bound is not. And this goes back to that question earlier, like, should I make my lower bound tight? I would argue not, right? I would argue not, because if I made my lower bound tight, I would just get infinity and infinity, right? And infinity is not a very useful quantity when I'm trying to make my red approach my blue. So this is an argument for the fact that the lower bound here is more useful than my original upper bound, which is infinity for this problem. My original KL. Now, something else that I want you to notice here is that this quantity here looks oddly familiar, right? I've got EP of f. I've got EQ of some nonlinear function of f. So this is, not entirely unlike an integral probability metric. I mean, it's not quite, because you've got this asymmetry here because of this nonlinearity, but I've got an expectation of a function. I've got an expectation of a nonlinear mapping of a function. So this is kind of weird, because I'm noticing that my KL, my lower bound, is acting a little bit more like an integral probability metric and a little bit less like a phi divergence, because a phi divergence here would just be infinite. But here I have this f function that, even though the density ratio is not defined, it can sort of tell me if red and blue are getting close, because it's smooth and it sort of interpolates between red and blue. And that behavior is a lot more like an integral probability metric and a lot less like a phi divergence. Can KL be written as an IPM formally? No, it can't, because an IPM has to be symmetric. So it's like an IPM. And in fact, give me a couple of slides and I'll give you even more information on how it's like an IPM. But that's a very good question. Okay. Now, is it the case that it's always a win to use this smooth function class? Well, careful, okay? So there is some, obviously, if I'm training a generative model, I have to do something like this. But there's also a pitfall to doing something like this, which we're going to see next, okay? Let's say that P and Q do have a well-defined density ratio. So here, P and Q are both Gaussian, and Q, the red one, has a narrower variance than P, the blue one. Okay, now as I move along the x-axis, red gets more and more narrow, and the KL, the true KL, has to explode, right? It's going up and up and up, all right? So that's this green line here. It's going up as my red gets more and more narrow with respect to my blue. What about the KL? What about the variational lower bound on the KL? I've required that my function is smooth, right? And I know that I can only attain the true KL if f diamond is equal to the negative log ratio of P to Q. Now, this negative log ratio is becoming less and less smooth as I move up this x-axis, right? As my red becomes very, very narrow, the negative log ratio becomes very, very non-smooth, right? It's very, very pointy. And that means that because I've insisted that my KL has a smooth witness function, that my f for my KL is a smooth function, my upper bound is going to get worse and worse as I move up this axis. So what that means is that I penalize this red being supported on a much narrower support than my blue less than I should do, or less than I would want to do, okay? This is something which is observed in training GANs, which is called mode collapse, which is that, I have my generator, it's being trained on a KL or a variational Jensen-Shannon or a variational reverse KL or a variational chi-squared, whatever you like, okay? And in all of these cases, there is a susceptibility to mode collapse. So there's a susceptibility that the generator putting its mass on too narrow a support with respect to the target. And these variational lower bounds don't penalize those maybe as much as they should be doing. So that's just something to be very careful of. You have to use the lower bound. There's no choice if we're in this scenario here. But this lower bound also has, let's say, a shortcoming. And the shortcoming is that it's less, let's say, sensitive than it should be to this problem of mode collapse. Okay. All right. So we're now going to look a little bit more formally at some mathematical properties of the KL. One is now, remember with the MMD, when we had a rich enough class of witness functions, we knew that the MMD was 0 only when P and Q agree. We know that the KL is 0 only when P and Q agree. What about this lower bound? Okay, now if the lower bound is vacuous, like here's a vacuous lower bound on KL, it's just 0 everywhere. Okay, but we want this lower bound not to be vacuous. We want this lower bound to be 0 only when P and Q agree. Under what circumstances is it the case that the KL has this property? Okay, that it only hits 0 when P and Q are exactly the same. This is the case when the functions that we use to compute it are close to the space of continuous functions with respect to infinity norms. So at every x that you might evaluate them at, I can get arbitrarily close to a continuous function. Now, if that is the case, then my function class is rich enough that it will always detect that P and Q are different. So it'll only be 0 when P and Q are the same. What function classes might have this property? Well, reproducing kernel Hilbert spaces with so-called universal kernels have this property. So the exponentiated quadratic kernel, again, is a universal kernel. So that's a kernel which induces a function class which has this property. What about if I use neural nets? Well, if I use as my neural net class the ReLUs evaluated on affine function, and I take the span of these functions, so the linear combination of all possible WTX plus Bs, then this is also a rich enough function class, which I can use to detect that P and Q are 0, P and Q are different. Okay, this is more of a mathematical curiosity because I can't obviously take all possible ReLUs of affine transforms of my X, but it still tells you that with the neural network function classes, I'm able to construct a rich enough class H to detect any difference in P and Q, even though only in theory. Could you start with the KL and then switch to KL once the supports overlap? So that depends on the problem, right? So if I'm in a scenario where I might, once I've trained my generator well enough, have overlapping support, then yes. I would be careful though, like in the image generation case, that's not going to happen. So in that case, you wouldn't be able to do that. So that's to answer that question. Okay. We want another property though, and this property is closer to the property that we've seen for integral probability metrics. So this is getting back to this question that I got earlier about how integral probability metrics and these variational lower bounds relate to each other. Okay, now remember that we had this very nice property of Wasserstein and of MMD with a characteristic kernel that they metrize weak convergence. So if Q is converging weakly to P, then these distances are going to 0. Okay, this was a very valuable property. Does this property hold for the KL? Okay, it does as long as my class of functions I'm using to compute the KL is rich enough, so or is has a good smoothness property, let's say. Okay, so I need in addition to the properties of the previous slide, which is that it's a large space, I need the H to be Lipschitz in the input with constant L. So if let's say that my points move apart by some distance, then the functions evaluated at those points divided by the distance between the points should increase by no more than L. Okay, it's a smoothness constraint on my H. Okay, if this property holds, then KL will go to 0 if Q converges weakly to P. This is a very, very valuable property. Okay, let's understand this. Okay. Here is my KL, and I'm going to basically prove to you why this is the case. Okay, here is my KL. My KL is EP of F minus X minus F dQ plus 1. Okay, the proof is very simple. All that I'm going to do is to add and subtract the integral of F dQ. Okay, So here I've added the integral of f dq. Here I've subtracted, right, because there's a minus sign here, the integral of f dq. I've added and subtracted the integral of f dq. Very simple operation. But then I noticed something. Thanks to the properties of the exponential function, this quantity here is always greater than or equal to 0. Okay? Now I've subtracted off a quantity that's always greater than or equal to 0. That means that I can remove this term and get an upper bound, EQ of f minus EP of f. And this should look familiar to you, right? Because EQF minus EPF is an integral probability metric. So I've shown that my Kale is always upper bounded by an integral probability metric. And if this Lipschitzness property holds, I can in turn upper bound that by the Wasserstein distance times L. And I know that the Wasserstein distance goes to 0 when Q converges weakly to P, which means by this chain of upper bounds that the Kale goes to 0 when Q converges weakly to P. So this is an enormously helpful property because it tells me that unlike the original KL, which isn't even defined when P and Q don't have a ratio, this lower bound acts a lot more like an IPM. It acts so much like an IPM that you can upper bound it by 1. Okay? And this is a property that if I'm using the KL as a critic function for training a generative model, this property is enormously helpful. Okay, because it means that I've got a helpful teacher, not a teacher that just yells at me. Yeah, I hope that's clear. Okay, so this is a fantastic property, and right at the start of the talk, I argued that feed divergences, as used in practice by machine learners, are actually acting more like integral probability metrics. And here I've made this a little bit more formal, and this is a property that actually makes them useful if you're using them to train GANs. All right, so I'll pause here just briefly to take some questions, but the next part is how, I've talked about critic functions, I've talked about IPMs, I've talked about feed divergences. Now let's use the critic function to train a generative model. So that's the next part. So I'll just have a brief pause in case there's a question before I start talking about that. But we've had quite a lot of questions, which is great. So I would be disappointed if there's no more yet. All right, very good. Okay, let's continue. So how to train your generalized energy-based model? And I've crossed out GAN here. Like, we know how to train a GAN, right? I'm assuming everyone has encountered GANs before. So let's just give let's say, visual reminder of what a GAN is doing. Okay. So a GAN has two components. It has a generator, a little student here, and a critic, a teacher. Okay, the generator generates a bunch of samples. Okay, in this case, the task is to learn to draw pictures of dogs. So the generator generates a bunch of pictures of dogs. The critic function takes a set of generated dogs, compares it to the set of real dogs, and gives feedback to the student. And this process cycles and cycles until eventually it reaches some equilibrium. Okay, so this is like the cartoon version of the GAN. I've got my student, I've got my critic. What do we do after we have trained a GAN? Well, we take the critic, we throw it in the trash, and then we keep the student. But this seems very wasteful, right? Because unless the student has learned to perfectly draw dogs, the critic is going to know something about the difference that remains between the student's dogs and real dogs. And we're throwing the critic away. It seems a mistake, right? The critic has information. Why shouldn't the critic help in generating dogs to guide the samples towards a good part of the space? So the purpose of generalized energy-based models is to somehow include the critic in the generating process to improve it. So thank you, Heba, for that kind comment. But I'm too modest to repeat it for the audience. Okay, so let's remember how the generator works. The generator takes a low-dimensional noise source, passes it through a bunch of convolutional filters, and outputs a high-dimensional function, G, which is an image, okay? In our case, maybe a picture of a dog, okay? So we know by construction that the output of the generator, even though it's in very high dimensions, can have no higher dimension than this noise source, right? It's on a low dimensional, let's say, submanifold in this much higher dimensional space. Okay, so this is what the generator is doing. And the question now becomes, can I somehow use a critic to improve that generator? If I train my GAN, I've got my generator, I've got my critic, do I have to throw away my critic? Or can I somehow use that critic to help this generator? And if so, where in this pipeline can my critic help me? Okay, so I'm going to first of all describe what I want my generalized energy-based model to do. And then I'm going to describe why it is that the critic function from the GAN, in particular the KL, the variational lower bound on KL, achieves that goal. Okay, so it's going to be first what, like what is it that I want to achieve? And then why. Why is it that my KL critic achieves that goal? So keep this, let's say, framework in mind as I describe the problem, okay? I'm going to illustrate this with the simplest toy problem I can think of, which still has the properties that I need to illustrate how my critic can help me, okay? So this is a problem where P is in a one-dimensional submanifold in a two-dimensional space. So remember that fundamentally the situation we're in with images is that we are in a low-dimensional subspace of a higher dimensional space. Now, the only way I can visualize this easily on a slide is to make my high-dimensional space 2D and my low-dimensional space 1D. And that's what I've done here. Okay, now in this example, how do I generate this P? I draw Z uniformly on 0, 1. I distort Z so that it has more mass towards the ends and less mass in the middle, okay? And then I take that one-dimensional signal and map it to 2D by putting it on this wiggly line here, okay? That's this G theta style transform. Okay, this is my target. This is what I want my GAN to generate, or my generative model generally to generate. Now, what if I were to use a classical energy-based model? So the off-the-shelf energy-based models, what do they do? An energy-based model defines a density, P of x, proportional to the exponential of the negative of an energy function, okay? Now, the, let's say, limitation of an energy-based model is that this energy function has to be a function over the whole domain x, right? Which means that P of x has to have a density on R2, okay, in this case. I've sort of put a Gaussian blur around my G thetas, around my mapped points. Now, you can see the result here, right? I've got this sort of thing that follows the support. It's put less mass here, as it should. It's put more mass on the ends, also as it should. But it's a little bit blurry, okay? Now, in low dimensions, maybe that's not a disaster, okay? In low dimensions, a little bit of blur, it doesn't hurt. What about if I'm generating images? Well, blurry pictures of dogs are not great, right? I'm not going to be able to publish that in ICLR. So these classical energy-based models, because of this sort of blurry property, because they need to have densities over the ambient space, over this X space, they're not going to be great. Okay? So thank you for the kind comments. Yeah. So these are classical energy-based models, and we've seen their limitations. Now, I'm going to next give an example. I'm going to give a break actually very soon. This is the plan. So please don't worry. I'm planning it basically at 10:30 at the halfway point. So don't worry. I'm not going to force you to work through the whole thing. Okay. Okay. So here is what my GAN is doing. Okay. I've basically defined here a GAN which is deliberately underpowered, okay? My GAN is going to do the following thing. It's going to take a low-dimensional source of noise in 1D. It's going to pass it through this nonlinearity. But what it's not going to do, what's missing here, is the capacity to put more mass at the ends and less mass at the middle, right? This tau part is not within the power of my GAN to represent, okay? So what that means is that my GAN, by deliberately being underpowered, it's going to put support in the right place. It's going to put mass, let's say, on the right support, okay, on this wiggly line, but it's not going to put more points here, not going to put fewer points here. So it's got the support correct, wiggly line, but the mass wrong. Not more points here, not fewer points there. But somehow what we want is for our critic to do the following thing. Our critic needs to importance weight the mass that my GAN put down. So I take my x's that my GAN put down, and then I weight them only on this line by e to the minus energy, okay? Unlike an energy-based model, which just puts E on the whole space, I've weighted the points on the line by this energy function, okay? Energy function is defined on the whole space, but I only care about its value on this line. And this energy function is going to be able to take what the GAN did and to, let's say, correct it so as to put more mass at the ends by putting more, like lower energy at the ends, and less mass at the middle by putting higher energy in the middle. So this is going to correct what my GAN did. So if, and I haven't said how this is going to happen yet, if my critic can somehow achieve this, then I'm going to be able to, let's say, correct my generator and get something closer to my target. All right. So I think, as I promised, this is a good point for a break. So let's, I'm not sure what the normal amount of time for a break is. Maybe if you give me some guidance, I can break for that amount of time. Because I think this is a good cliffhanger. Like, how do I achieve this using a critic? We're going to find out soon. Is the energy function constant in the space except for the line? No, it is not. We're going to see shortly that it's not. We only care about its value on the line, but the energy function is still going to be defined on the whole space. And that's going to be very important. It's going to be very important in the event that maybe my generator isn't hitting the support perfectly. Maybe it's close. If it's close, I need the energy function still to be defined on it. Okay. Yeah, so let's, we're going to resume like the actual lecturing in 10 minutes. But in the meantime, I'm happy to just chat with people. If you type things in the chat, I can sort of talk about whatever people ask me. Okay, I think people, yeah. Yeah, so how to choose the right divergence? So there's, I think, because there are indeed so many divergences, there's Wasserstein, there's MMD, there's Hellinger, there's chi-squared. In a sense, like there is no one divergence to rule them all. So all of the divergences have strengths and weaknesses. So for example, Wasserstein is great for, let's say, transporting mass from a source to a target. Like that's what it's designed to do. Wasserstein is hard to compute in high dimensions, although Marco Couturi has done like extremely valuable and I think interesting work in approximating Wasserstein distance efficiently in high dimensions using this synchron method. Hellinger versus chi-squared, in a sense, it's like it's very sort of hard to know in advance like which method works best. Not least because you might be using lower bounds on them, which then sort of like drift you a little bit away from the original properties. So in a sense, like my sort of off-the-cuff answer would be, look at the problem you're trying to solve, try the different divergences and see what works. So I'm not so familiar with Carl Friston's work. So the question was what my thoughts are about free energy minimization by Carl Friston. I don't know enough about Carl's work to be able to comment intelligently on it, I'm afraid, even though he's also in London. So that's my answer to that question. So sorry not to have more to say about that. Okay, so the question is, what are my thoughts on using energy-based models in combination with deep neural networks to allow an approximation of general complex distributions? So perhaps it might help if you tell me which references in particular you have in mind. Okay, cool. So Roman will post references. I mean, it may be that I haven't read them, so I cannot promise to have an intelligent answer, but at least I'm interested to see. I'm always interested to see more work in this area. So please, yeah, show me. This is a very good question. So indeed, like I'm taking my Z. The question is, in the GAN, you push forward a d theta. I use b theta as a push forward, and the probability density requires this Jacobian. So, one of the sort of merits of the GAN is that in generating samples, I don't have to worry about the Jacobian because I'm just taking a noise source, pushing it through some set of transforms, and getting out a sample, right? Now, what's going to be interesting is that when I use the critic to do importance weighting, I still won't have to compute my Jacobian. And this is, I think, a very important property. In particular, like, it might be exceptionally difficult to get a Jacobian of a transform from a low-dimensional noise space to a high-dimensional ambient space where I'm covering a submanifold. I mean, that's a very difficult computation, which is why, like, normalizing flows are so popular, because they have this very simple Jacobian. Fortunately for us, we won't have to worry about the Jacobian in our setting. To take the questions in order, is there a question for choosing the right kernel? Yes, there is. That's the final part of the talk. I will talk more about that than you will probably have the patience to hear. So don't worry, there's plenty of material coming for that. Okay, in the recent slide, the energy-based model cares about all the points in the space. But we reweight the points we want. That's exactly right. Okay. So let's look at the slides. The energy is defined over the whole ambient space, but we only care about its value along the support of the generator sample. Okay. So it's only where the generator is placing mass that we care about the value of the energy function. Whatever it does elsewhere is not our problem. Okay. I see a reference for that. Let me just click on that and see what it does. Okay, so I don't know this paper about 3D object detection using energy-based models, but it looks like it should be. I should be aware of it. So thank you for bringing that to my attention. And I'll have a look at what it's doing later. But I haven't read that paper yet, although I do know Gustafsson, actually, as it happens. So I'll have a look. Right. So is it correct that the only difference between MMD, exactly. So basically, like, MMD and Wasserstein are both integral probability metrics. And the difference between the two integral probability metrics is the class of functions that I use. So I can use class of functions with solutions not bounded by 1. I can use MMD. I can use the MMD, which is the RKHS norm bounded by 1 as my witness class. But in all cases, I'm looking at the difference in expectations of f, some function f from a class, under P and Q. Okay, and so in the difference between the ITMs, each ITM is characterized by the function class that I use when I'm defining my expectation under P of f minus expectation under Q of f. Okay, energy-based models for T probabilistic regression. Let me have a look at that. Okay, so again, I'm not familiar with this work, but it looks like I should have a look at it. So thanks once more. So I've got these now in my web browser, so I'll have a look after the talk. So thank you for sending me these. Okay, so if we're having a 10-minute break, I think we have, let's say, 1 more minute. So I'll start in 1 more minute. So if you are having a coffee, you should finish your coffee. Okay, so what do people think? Are we ready to embark on the second half? Okay, I have confirmation, so I will continue. Okay, so as always, I'm monitoring the chat, so please ask questions whenever something is not clear, and I'll do my best to answer. Thank you also for the references. I mean, this is really helpful to me because the field now is obviously huge, and I'm always very excited to discover new work, particularly in the energy-based model space. Okay, so let's remind ourselves of our goal. Okay, our goal was we want a way of generating samples that match a target distribution. Okay, we have a generator that, let's say, has got the right support, but it's missing something. Okay, I've made it deliberately weaker than it needs to be, and what it's missing is the capacity to put more mass towards the edges of this wiggly line and less mass towards the middle of this wiggly line. Okay, so it's basically placing uniform mass along this wiggly line rather than more mass at the end and less mass in the middle. And what we therefore want to do is to somehow define an energy function on the space X, which we evaluate only along where my generator places support. Okay, so it's defined on the whole ambient space, but I'm evaluating it only on this wiggly line. And this energy function should reduce the amount of mass that I place in the middle and should increase the amount of mass I place on the edge. Okay, and if I can take my generated samples and reweight them by this energy function, then I'm going to have something that matches my target better. And I claim, and I haven't told you why, that this energy function is going to be given to me by my KL critic. Okay, so if I include the KL critic in my generating model, that amounts to using this energy function to reweight my samples. I haven't told you why, I've just claimed that this is true. Okay, so let's show in math what I showed in figures in the previous slide. Okay, I define a model which has two things. It has a generator, B theta, and it has an energy, E. Okay, the generator is just my standard GAN generator. I sample a Z from a low dimensional noise source. I push it through a B theta, parameterized by theta. That's my neural net stack from earlier. And then out comes an image, a picture of a dog. Okay. Now here is where things get different from a standard GAN. I take these x's and I reweight them according to some importance weights, which are given by exp minus E. Okay. E is defined on the whole space, but I only evaluate it at the points which come out of my generator. Now I need my probability to sum to 1, so I have to normalize it by the integral of this energy function over Q. Q being the probability defined implicitly by my generator here. Okay, so I need to divide by this normalizer to make sure that my density is still a valid density. Okay, so my model has two components, generator, energy function. Now, if it so happened that Q had density on the ambient space, like Q was a Gaussian, I would be back to standard energy-based models, and we've seen that a million times, and you know that's very well understood. Where things get interesting is when X is on a low-dimensional subspace of my high-dimensional space, as happens when I'm generating images. It's always true for that case. Okay, right. So this is what I want to achieve. Okay, this is what I want my generalized energy-based model to do. When I say generalized, it's because the energy is defined here or evaluated here only on this submanifold of points where Q is placing mass, right? As opposed to on the ambient space, which would be an energy-based model rather than a generalized energy-based model. Okay, so that's the distinction I'm trying to make here. Okay, so let's look at this example again. Here is my target. Remember, my target is placing more mass on the ends and less mass in the middle. Okay, here is my generator, my GAN generator. It's got the support correct in this case, so it's placing mass along this wiggly line, but it's not placing more mass at the ends and less mass in the middle. Okay, correct support, wrong mass. Now here is my energy function. As I described, I'm showing it as a contour plot here, so you should think of this as a sort of mountain surface, okay? I haven't told you how to get it, okay? But this is the energy function that I'm getting for this example. I evaluate that function only along my red line, and blue means push the mass down here. Orange means push the mass up here, okay? So what my energy function is telling me is push the mass down in the middle, push the mass up at the ends, okay? This is the log energy function for my example. All right, and so this is, this is how I'm ideally going to solve the problem that I described on the previous slide. I'm going to somehow, and I haven't told you how, compute this energy function so that it pushes down the mass here, pushes up the mass there. Now, a subtlety here is that that energy function is evaluated only along the red line, but it's defined on the whole space. And this is important. Okay, why is this important? Well, let's say that my generator is even more incorrect, okay? In this case, my generator has not only the wrong mass, but it also has slightly the wrong support, right? So let's say my generator is close to where it should be, but it hasn't quite got there. In this case, I said that my generator is a little bit too smooth. So it's trying to approximate this wiggly line, but it's a bit smooth, so it can't quite get there. In this case, I can still evaluate my energy function. I can still compute my energy function, and I can still evaluate it along these red points. And it's still telling me to push the mass down in the middle and to push the mass up at the ends. Where one should be a little bit careful is if my generator drifts a little bit too far from my target, then maybe the signal that I'm getting from my energy function is no longer very helpful. So, I need to be reasonably close to my target for this to be useful. But as I get close to my target, my energy function, defined over the whole space, is still useful. It's still pushing down the mass where it should, and it's still pulling up the mass where it should. Okay, so this is the picture you should have in your head when I'm saying that I'm using the energy function to reweight the samples that occur on this red line here. This is what you should be thinking of. Okay, I'm computing the energy function on the whole space, but I'm using it to reweight the points on my target. And this is, I think, really exciting because it's very challenging to sort of think about how to, let's say, importance weight generated samples in high dimensions. But I'm claiming that my energy function here is able to achieve this and to make Q closer to P as a result. Okay. The question came up how to compute the integral. Do you mean this integral here, the normalizing integral? Is that correct, Roman? The answer to that question, if that's your question, is you don't have to. We're going to see, well, we're going to compute this integral, but we're going to do it by solving an optimization problem. So you're going to see how we do that shortly. But that's a very good and very subtle question. Okay, so this is my generalized energy-based model, right? I have a mismatch of support between my generator and my target, but even so, my energy function is giving me helpful importance weighting information. Okay, to answer Roman's question, how do you compute this normalizing integral? I'm going to show that very shortly, and it's going to be part of the solution to an optimization problem I'm going to solve. Okay. So this is my generalized energy-based model. So how, I've shown you what we want to do. How do we do it, right? How do we learn this energy function E? Now, I've claimed that we're going to learn the energy function by keeping our critic when we're using the KL as our critic. Okay, so in the next couple of slides, I'm going to show you how to do that. Okay, now, fundamentally, we're going to learn the energy function by maximizing log likelihood, as you learned in your standard ML 101. Okay, and I'm going to basically maximize the expectation of the log of FQE, right? The log likelihood of my model, incorporating my generator, my energy under P. Okay, so to expand that out, when I've got my model that I defined a couple of slides ago, that amounts to maximizing minus EDP minus log Z, right? Where Z is the normalizer, okay? Now, first of all, let's say that the ratio of P to Q is well defined, okay? Let's say that Q has a density, P has a density, ratio of P to Q is well defined. In that case, we get back a very well-known lower bound on the KL, which is called the Donsker-Varadhan lower bound, and it's tight when the energy function is the negative log ratio of P to Q. And this totally makes sense, right? Because I've said in this setting that E is an importance weighting distribution. So when does importance weighting work? It works perfectly when the importance weights are the ratio of P to Q. And because I've got this exponentiation here, I have to take the log. So if E is negative log ratio of P to Q, then I get back importance weighting in the classical setting. Right? So this is just to, let's say, express what this becomes in the event that P and Q have densities and the ratio is well defined. However, I care about this setting here, right? P and Q don't have densities and the ratio is not well defined. It's not even defined, right? It's infinity. And yet, this quantity here still makes sense as long as I have a smoothness constraint on my E. Okay, as long as E is smooth, this is the key, right? If E is smooth, then P and Q don't have to have densities. Ratio of P to Q density doesn't have to be defined, but this quantity still makes sense. Okay, and this energy function can still be used to make my red distribution closer to my blue distribution. All right, so this is a subtle point. This is the quantity that I'm going to optimize to get my E, but this still doesn't look like a critic function. So to see how this relates to the critic function, I need one more slide. Okay, and that's this slide here, which is going to show that I can optimize KL to get my energy function. So here's my generalized log likelihood from the previous slide, minus EDP. And remember, minus log Z, well, I'm going to substitute here minus log integral x minus EDQ. Okay, this is what I want to solve to compute my energy function. Now, this log sum x is a bit of a pain. So rather than computing it, I'm going to use one last trick, which results from the convexity of the exponential, which I can lower bound log sum x with minus c minus e to the minus c exp dq plus 1. Okay. Now, this requires a couple of lines of algebra, which I'm not going to show in these slides, but you can do this for yourselves this evening, and you can convince yourself that this is a valid lower bound on the exponential. And the lower bound becomes tight when c is equal to the normalizing constant. Okay, so if I've solved for c, I now need to, let's say, optimize for c as well as e. And if I optimize for c and c attains this, and I optimize for e, then I get exactly my original expression again. Okay, so let's substitute this lower bound into my expression. Now I have minus e plus c dp minus e to the minus e minus c dq plus 1. And this should look familiar. And in fact, it's a Kale. Okay, so now I've shown that if I use a Kale as my critic, and if I, let's say, separate out this constant offset term when I compute my Kale, then I get an energy function out, which I can use to reweight my samples. Okay, so if I use a Kale critic, I get an energy function. And now I've connected my Kale from the first part of the talk with the energy-based models in the second part of the talk. This is what gives me my energy function. So I'll train with a Kale as my critic, then I'll take the energy function from my Kale, I'll use that to importance weight my Q samples, and out is going to come a better set of samples than I started with. This also answers the question that Roman posed earlier. How do I compute this normalizing constant? Well, when I'm computing my energy function, I'm also optimizing my C. And in optimizing my C, I get an approximation to this normalizing constant here. It's not that important. I don't, in fact, need it, as we're going to see later, but it's something that we do get out of this process. Now, this is a very important slide, so I'm going to pause here for questions. Is everyone happy with this slide? Okay, I'm computing the Kale. I'm using the Kale as my critic. I'm getting an energy function from that Kale, and then I'm going to use that energy function to weight my samples from my generator to make them closer to my target, exactly as I showed on this nice contour plot here. Are there any questions about that? Okay, that's the Kale divergence. Okay, perfect. Very happy to hear. Great. Okay, so I'm using my Kale, get an energy, boom, done. Okay, and C star, which I'm also going to optimize because I'm sort of separating out my constant term from my in my Kale, is going to approximate this normalizer. Okay. Actually, I'm going to skip this part. The one thing to remember, right, when I'm doing again, right, I alternate. I train my generator, I train my critic. Okay. And when I'm training this generalized energy-based model, I do exactly the same. I alternate between training my generator and training my energy function, training my Kale. One thing that I should do is I will generally take, and this is actually a common practice when training GANs, I take more steps in my generator before I update my energy function. And this is actually well justified in theory. I'm not going to say why, because that would be a bit of a digression, but this is something that is supported here. Okay, let me skip that slide. Okay, so I've told you that the Kale gives me an energy function and that I can use the energy function to reweight my generator samples to make them closer to the target. That's a very good question. So the question is there any use of C for Bayesian model comparison? That's a great idea. You should try it. I haven't tried it, but that would be something fun to try. Okay. Now I've claimed that we're going to use the energy function to importance weight our generating samples. Now in practice, importance weighting is very inefficient. It's inefficient computationally and it's inefficient statistically. It gives high variance and it's a wasteful procedure computationally. So a question arises then, is there a way of doing importance weighting without doing importance weighting? That seems paradoxical, right? Is there a way to somehow have the same effect as doing this importance weighting by my energy function without actually having to importance weight my samples? And this slide answers that question. The answer is quite subtle, but very satisfying when you see it. The answer is yes. Okay? The answer is yes, because I can modify my generator distribution, the noise distribution for my generator, in such a way as to have the equivalent effect of doing importance weighting. So I'm never going to do importance weighting. What I'm going to do is I'm going to tweak my generator distribution, my noise distribution to my generator, and that's going to have the same effect. Okay, so it's sort of saying, let's sample more points from good parts of my generator noise space and fewer points from bad parts of my generator noise space. And that's going to result in the same effect as doing importance weighting. So that seems a remarkable thing to be able to do. But actually, the justification for this is very simple. And I'm going to show you this on that slide. Okay. The way to understand how this can be done is to think about what would happen if I computed the expectation of some function g of x under my distribution here, which contains my generator and my E. Okay. So what would happen when I computed this expectation? Well, I'd compute g of b of z, right? I compute g on this z point, push through my b, weighted by my f, right? Where f, which is my energy function with this normalizer, would be computed by, would be computed on b of z, right? So that's this importance weighting distribution. And then integrated over e to z, which is my noise distribution. Okay, so this is what I would do if I wanted to compute expectation of g. Now, equivalently, I can think of this as giving me a posterior distribution over z, okay, my latent noise distribution, which is eta reweighted by f of b at z, right? So if I sampled z according to this posterior, then pushed this z through my generator, this would amount to giving me the right distribution over z for computing expectation under my model, okay? So this is the modification that I would need to make to my noise distribution to get the right noise distribution to give me samples with this importance weighting effect. And you can see this just by this simple equality here. Okay. So a question might be, well, can I sample from this distribution? It seems hard, right? Because I've got this normalizing constant. But it turns out that there are many methods for sampling from distributions when I only know them up to normalization, as long as I can, let's say, compute appropriate gradients. So I'm not going to go into detail here, but I will just assure you that there exists many, many samplers to sample from this z distribution, which is being modified by this f, as long as I can take the gradient of f with respect to the energy and the b, which I can because, by design, I can do that using autodiff. Okay, so that means that I am now not going to be sampling from eta. I'm going to be sampling from this new distribution, which is modified. Then I'm going to push that through my generator. And then I'm going to get, let's say target samples, which are equivalent to having done this importance weighting. This is way more efficient. This is what you should do. Are there questions about this before I go on? So in a sense, like, these two sentences here, like I can sample from this distribution. These two sentences, like, let's say, encompass a very vast literature on sampling from distributions. And to implement this in practice, I advise you as a first step to download the code that we put online and to try it. But there are many, many methods for sampling from these distributions. So it's a very large literature. And that's a lecture in itself. But the upshot is, I can modify my noise distribution for my generator by this quantity here to have the equivalent effect of doing importance weighting. And it sort of upweights good parts of my noise and downweights bad parts of my noise. Are there questions about that before I go on? Great. Okay. So now let's look at some pictures. I'm going to show two things, okay? First of all, I made a claim at the start of the talk. I claimed that if I use the critic function as part of my generating model, I will always do better than using the generator alone. Okay, I'm going to illustrate this on this slide for many data sets, CIFAR10, LSUN, CELAB, ImageNet. I'm going to have a GAN, which is going to be for each of these examples here. And then I'm going to, let's say, modify this GAN by incorporating the energy function to importance weight my samples. Of course, I don't really do importance weighting. What I do is I do this trick that I described on this slide. So modifying the noise distribution to have the equivalent effect of importance weighting. But I'm claiming that I'm always going to do better than I would have done if I just thrown away my critic and used the generator on its own. Okay, so here's 4 settings, CIFAR10, LSUN, CELAB, ImageNet. Here is the FID score. So this is a measure of performance for GAN samples, and lower is better. Okay, now I'm going to compute here a normalized FID score where 100 corresponds to the case where I've just used a generator. So this is sort of like the baseline. Okay, now red here is what I get when I include my critic. I don't throw it away. I include it. I use the energy function that my critic gives me to modify the noise distribution of my generator. And every single case, I get better performance. Okay, so this is quite remarkable because like this is across the board. These examples here are ways of modifying the noise of my generator to push myself towards better parts of the space using the energy function. And these heuristics improve, but using this approach here improves more. And it's in a sense, it improves more because it's an end-to-end model. It's basically using the energy function to create an energy-based model, which incorporates the generator. So this is improving over these heuristics, which are sort of local search heuristics. Could I use a normalizing flow? So using normalizing flows to generate images, that's a difficult art. I believe there may have been recent work where this has been I think done a little bit better, but one has to be a little careful because remember that images are very high dimensional. That means that Z has to be very high dimensional, indeed, as you've said in your question. And as a result of that, I don't want to get blurry images. I want to get sharp images, and it's quite challenging to achieve that with normalizing flows. Though I'm obviously not an expert in the state of the art for normalizing flows, so there might be some ways to do that. But these generalized energy-based models are going to give you sharp images. The other thing that you can do, why would we need to sample the noise, right? So when we draw samples from a GAN, right? When we draw samples from a GAN, we take Z from some noise distribution, we push it through a generator, and we get out a target, a picture of a dog or a bedroom or whatever, okay? Now, an energy-based model reweights those samples, so it pushes up some regions and pushes down other regions in my image space, right? It makes some images more likely, other images less likely. I have claimed in that slide that the equivalent effect can be achieved by modifying the noise distribution. So rather than using some generic noise distribution from my GAN, I modify the noise distribution by this function here, which pushes up some region of my noise space and pushes down other regions of my noise space. So that means that I'm more likely to create good samples according to my critic and less likely to create bad samples according to my critic. So this is what I'm now doing to modify my noise distribution from my GAN to give better samples. And this improvement is informed by my energy function, my critic function. So the claim is that by including the critic function, unless the critic function is perfectly flat, unless it's completely uninformative, including the critic function is always going to improve my samples, right? Because my critic function tells me something about where it is that my generator is still making mistakes. And in practice, this is borne out, because in practice, we're getting better performance if we include the critic function than if we throw it away. So here is a kind of interesting example, which is going to take a little bit of explaining. So remember that I'm sampling in my noise space, and I'm sampling in my noise space using this Langevin approach. Okay. Now, what that means is that I'm sort of doing a random walk in my noise space that's biased towards regions that give me good samples. Okay, so I've got little modes in my generated noise space that give me good samples, but as I move from one mode to the other, I go through regions of low probability before I get stuck on other regions of high probability. And what I'm showing here is the path that my sampler is taking through the noise space of my generator. And you can see that sort of like it's going to cars, and then it's moving to a low probability region, then it's going to some wildlife picture, it's going to a low probability region, then it's moving to another car. Or here's another path, okay? So it's starting with cars, low probability region, then some urban scene, then low probability region, then some nature scene. This is kind of interesting because I can sort of see the path that my sampler takes as I move around different parts of my noise space and I explore the space of samples that I can get. Now, obviously, you know, I'm interested in when the sampler hits a peak in the noise space, but I can also sort of run it through the low density regions as well. And it goes sort of from peak to peak to peak and generates different samples around my space. What noise distribution am I using in practice? So I start with just a Gaussian noise, but then I modify it, obviously, using my energy function here. Yep. And this modification is very important because it results in biasing my noise towards good parts of my space and away from bad parts of my space. Okay. So I urge you, so I've obviously encouraged you to use the critic function to improve the generator. We have code online, so please look at this. Now, I should emphasize as well, like this idea of using energy functions to improve generators is something that is a very lively area of research in, let's say, the last year. So basically, within a couple of days of us publishing ours, Mila also made the same approach or proposed the same approach, in their case, using the Jensen-Shannon rather than the Kale, okay? So this is a paper that they have also put forward. It's a fantastic paper. You should definitely read it. What they've got in this paper, which I haven't talked about, which is, I think, very exciting, is what happens when you use integral probability metrics to get an energy. Okay, I haven't talked about that at all. They have that in their paper. So this is something I think very exciting. There's also two ICLR papers that appeared this year, which also describe this notion of using the energy function to refine where the generator places mass for autoencoders or for deep generated models. So again, like these are great papers. I urge you to read them. So there's a lot of work in this area. There's a lot of work in this theme of using a critic function to refine a generator. And so, you know, this is I think an exciting area to develop. So I'll take a quick pause here before I go on. Are there any questions? Okay. It looks like there are no further questions for the start. Okay. So in the next part of the course, I'm going to talk about the final problem that I discussed, which was if I've got, let's say, two samples in some very high dimensional space, I want to learn, I want to determine whether these two samples are from the same distribution or from different distributions. And a reason for doing that is that let's say that I've trained on one sample and I'm deploying on another sample. If these distributions are different and I train on one and I deploy on the other, well, that's probably not a good idea. It's probably going to mean that I'm going to start making errors. So this is an important diagnostic tool. If I train on CFAR 10, test on CFAR 10.1, if CFAR 10.1 has a different distribution to CFAR 10, that's not great, right? And so it might be that I then run into problems. So I'm going to use MMD to compare CFAR 10 and CFAR 10.1 ultimately. But to do that, I'm going to have to be very careful in my choice of kernel, because this is a very challenging problem. And I'm going to need to choose a good kernel to solve that problem. And for that, I need to sort of find the kernel that gives me an MMD that is best suited to distinguishing P from Q in this very complex domain. This is a hard question. It's a question that bothered me for many, many years. So it's not a question with a trivial answer. Okay, so let's remind ourselves what the MMD looks like, right? The MMD has two different forms. One is as an integral probability metric, as a function, a well-behaved function that maximizes the difference in expectations under P and Q, okay, a smooth function. The other is the norm of the difference of feature means, okay, feature mean of P, feature mean of Q. It's this second form that we're going to be using for the rest of the talk. We're not really going to be thinking much about this integral probability metric form. We're going to be really focused down on this difference in feature means form. Now, this is the form that's going to be most useful to us when we're going to think about how to best choose our kernel to distinguish samples from P and Q. Now, I've shown you earlier how to compute this witness function, but what I didn't show you is how to compute the MMD. When I'm computing the MMD, it's this form that's going to be best suited. Okay, so let's see how I can use this difference in feature means form to compute the MMD straightforwardly. Okay, I'm going to square it for reasons that will become clear. So here is my difference in feature means squared. I'm now going to compute the MMD. Now remember that like the key point that I want to emphasize is that even though I've got means of infinitely many features, I don't want to have to write those down. I want to express everything in terms of kernel functions, in terms of dot products between these features. Because if I can do that, then I don't have to worry about these infinitely many features anymore. Okay, so step one, the squared norm of a difference is the dot product of this with itself, right? Dot product of mu p minus mu q with itself. And I can then expand that out, right? So I get the dot product of mu p with itself, dot product of mu q with itself, and twice the dot product of mu p with mu q. Now remember that the dot product of anything with the expected features is just the expectation of the dot product, right? So I can then take this expectation outside. I got the expectation of my kernel, my features, my dot product between features of x and x prime. So x prime is basically a sample drawn from P, but independently of x. I've got my sample of k of y and y prime. So y is drawn from Q, y prime is drawn from Q independently of y. And I've got my expectation of k of x and y. So this has a very simple intuition, okay? Let's think of a kernel as a dot product between features, right? So a kernel you can think of at a high level as a measure of similarity. When my dot product between features is large, my objects are similar. When my dot product between features is small, my objects are different. So this is the average similarity between points drawn from P. Okay, I take one point drawn from P, I take another point drawn from P, I compute their average similarity. That's my first term. This is the average similarity of points drawn from Q. Okay, I draw one point from Q, another point from Q. How similar are they on average? And this is the average similarity of points from P to Q. Okay, so how similar on average is a blue point to a red point. Now, if on average points are similar within class, points are as similar within class as they are between classes, then all of these terms cancel and MMD is 0. Okay, but if points within class are much more similar to themselves than they are to points to the other class, then MMD is big. So this is a really nice and very simple intuition for what MMD is doing in terms of these kernel functions. So I'm going to show you what this looks like in the event that I have samples from P and samples from Q. Okay, so let's say P is a distribution over dogs, and Q is a distribution over a fish. Okay, each of these entries in this table here is how similar one dog is to another dog, or how similar one fish is to another fish, or how similar dog I is to fish J. So what do we see on this table? We see this dog and this dog are quite similar. So they've got a high similarity rating. This dog and this dog, well, they're not as similar, right? So they've got a lower similarity rating. This dog is very similar to itself, obviously, but that's kind of boring. Like we know an object is similar to itself. Likewise, we've got these fish. Like these two fish are more alike. This fish and this fish, I mean, they're still fish, so they're somewhat similar. But dogs and fish are very different. Okay, so if I take my kernel between my dog and my fish, my similarity between my dog and my fish, I'm never going to get a big value here. Okay, so how do I compute my MMD for these samples of P and Q? Well, I take on average, how similar is dog I to dog J? But I leave out self-similarity. I don't care how similar a dog is to itself. Like that's not an interesting question for me. I care only how similar is a dog to another dog, okay, on average, okay? Now I take the average similarity between fish I and fish J, again, leaving out self-similarity, and I subtract from this twice the average similarity of dog to fish. Now, obviously, dogs are more similar to dogs and fish are more similar to fish than dogs are to fish, so I'm going to get a big number here. Now, imagine instead of dogs and fish, I had dogs and dogs. Well, on average, similarity of dog to dog plus similarity of dog to dog minus twice average similarity of dog to dog is going to be 0, or at least something very small, okay? So in the event that I have just only dogs and only dogs, I'm going to get a number here which is much smaller. Whereas if I have dogs and fish, I'm going to have a number that's large because self-similarity is much larger than cross-class similarity. So is this definition of MMD, or this new way of thinking about MMD, clear to everybody? Or are there questions about that? Now, the key, let's say, trick that I use here is that the dot product between, I've got these infinite feature dictionaries, and I'm ultimately trying to find the difference in expectations of these features under P and Q. But I use the trick that the dot product between expected features under P and expected features under P can be expressed in terms of kernels. So I never have to write down these infinite feature dictionaries. This also gets back to a question that I answered right at the start of the talk. That question was, what is the computational complexity of computing MMD? We can see here that it's quadratic in the number of samples because I need to evaluate the similarity of every pair of objects, which is quadratic in cost. Okay, no questions. Fantastic. Okay, this is the MMD. So I like this intuition. I mean, it's so simple. Like you can explain this to anybody. Like I've got a measure of similarity. Are objects on average more similar to other objects of the same class than they are to objects of a different class? If so, the sets are different. If not, the sets are the same. So very, very simple. Okay. So let's say that I've computed my MMD from samples. How does that help decide if P and Q are close or far apart? Now, remember, I'm computing this from samples, so it's not going to be exactly 0. It's going to be small when I've got all dogs. It's going to be large when I've got dogs and fish. But I want to somehow draw a conclusion, given the sample quantity that I computed, whether, let's say, P and Q are close or far apart. Right. So I have a question. Does this work in high dimensions? Well, it does, as long as I have a measure of similarity. So I've used dogs and fish for a reason, right? Because dogs and fish are images in a high dimensional space. Later on, we're going to be looking at CFAR. CFAR is in a high dimensional space. So this quantity I can compute even when x's and y's are in very high dimensional spaces. They can be images, they can be strings, they can be graphs, they can be very high dimensional, very complex objects. I can still say if on average objects from the same class are more similar than objects from a different class, then it's likely that P and Q that generated these objects are different. Okay, now if I have more than one class, one could sort of think about, let's say, P, Q, R, S, and T, like many, many different classes, right? But that's, I think, outside of the scope of this lecture. I'm a little confused, Aska, about your question, I'm afraid. Community detection. So I think I'll leave the question of community detection. That's, I think, a question that is good for a discussion at the end of the lecture. So let's talk about more about application areas then. Okay. So I've computed this quantity from samples, and I've got a number, like 5. Okay. Is 5 big? Is it small? If I get this number, Does it indicate that it's very likely that P and Q are the same distribution? Does it indicate that it's very unlikely that P and Q are the same distribution? How do I make that call when I've computed this quantity from samples, right? What's big, what's small? Okay, to understand this, I need to understand how MMD is behaving when I compute it from samples. Like when I compute it from samples and it's sort of clustered around 0, then it's quite likely that P and Q are the same. If I compute it from samples and it's very far from 0, it's likely that P and Q are different. But to sort of say what's close to 0, what's far from 0, I need a threshold, right? I need to basically make some sort of threshold that tells me if I'm below that threshold, given how many samples I've seen, it's quite likely that P and Q are the same. And if I'm above that threshold, it's quite unlikely that P and Q are the same. So a question then becomes, well, what threshold do I use? What's a sensible threshold that allows me to make that call? So I'm going to talk about how to compute that threshold. All right, we want this threshold, C alpha, and we're going to choose that threshold to get a false positive rate alpha. So I'm going to say, well, if I've chosen the threshold, given the number of samples I got from P and Q, then 5% of the time, I will mistakenly think that P and Q are the same when they're really different, okay? So, that's a threshold that's going to be saying, below that threshold, MMD is small, in quotes. Above that threshold, MMD is big, in quotes. So below the threshold, I think it's very likely that P and Q are the same. Above that threshold, I think it's very unlikely that P and Q are the same. Okay, so let's see how we can get this threshold. To understand how to compute this threshold, we need to understand how MMD behaves when we compute it not exactly with infinitely many samples, but approximately with finitely many samples. And we're going to do a little numerical experiment to illustrate how MMD behaves. Okay, great, I'm glad that I answered the question. Okay, so let's say that I've drawn 200 samples from P and Q. Okay, I'm computing MMD approximately with 200 samples from each of P and Q. And let's say that P and Q are not the same, all right? So in this example, P and Q are not the same. You can see that Q has higher variance than P. They're Laplace distributed as it happens. And MMD times square root of n in this example is 1.2. That's the number we're getting, okay? For those who are familiar with statistics, the square root of n is going to be a flag which should alert you to something that's about to happen. But for those not, don't worry, you're going to see shortly. Okay, so 200 samples, computed MMD is 1.2. Let's run the experiment. Okay, so let's put this on a histogram plot. Okay, so on the x-axis, I'm plotting root n times MMD. On the y-axis, I'm plotting how many times have I seen that value. I've only done one experiment, so I've only seen one value from MMD, which is 1.2. So I've put a bar here at 1.2. Okay, now let's run the experiment again. Okay, I've drawn 200 new samples from P and Q, completely new, and I've computed MMD. And this time I got a value which is not exactly the same, but it's close. It's 1.5. So now I've got two bars on my plot, 1.2 and 1.5. Let's do it again. Okay, 150 times. Now I've got a lot of bars on my plot. 300 times, 3,000 times. This is interesting. My histogram is starting to look like a shape that I should recognize. And that shape is a Gaussian. Okay, so what we have here is a central limit theorem. MMD, when P and Q are not the same, is concentrated around its mean. And if I divide by the variance, which is dropping as 1 on n, which is why I use this root n scaling here, this approaches a Gaussian. Okay, so MMD is concentrated around its mean according to a Gaussian distribution. As I use more samples, this Gaussian will get narrower and narrower. Okay, it's going to be more and more focused on the mean. So when I say that MMD behaves like a Gaussian when P and Q are different, this is what I mean. If I do this experiment many, many times, I get new samples from P and Q, I compute the MMD, I put it on my histogram plot. This eventually is going to look like a Gaussian, converging around the true MMD. Okay, so what is the physical meaning of root n times MMD? So I'm just computing. I've drawn samples from P, I've drawn samples from Q, I've computed MMD, I've scaled by root n. And I've noticed that when I do that many, many times, I get MMDs that are close to the mean, but not exactly because I'm computing it from samples. And the error that I'm making, let's say the divergence from the mean that I'm getting, is Gaussian. Okay, so it's distributed around its mean, clustered around its mean in a Gaussian distribution. So that's the sort of typical behavior that I expect from MMD when P and Q are not equal. Okay? When I'm computing it from samples. I'm interested in computing it from samples because ultimately I want to get a threshold for the MMD when I compute it from samples. So this is interesting, but watch out, because I've said that P and Q are different. And actually the threshold that I'm interested in is for the case that P and Q are the same, right? Because I want a threshold that, when P and Q are the same, I'm below that threshold with high probability when I compute it from samples, right? So what happens? Right, so this is a probability density function, remember? So a probability density function can indeed exceed 1. So I'm somehow like, my histogram is just a count, so I'm not normalizing it, and I'm fitting a probability density function. Oh, this is a very good question. So is it really Gaussian distributed? Aren't negative values excluded? It is a Gaussian distribution, and negative values are not excluded. Very good question. I was going to say that for later, but I'll tell you the answer now, right? Similarity minus average PDQ similarity. Now, if P and Q are very close, quantity plus this quantity is smaller than value, right? By chance, I can get a negative value here, right? Because it just so happens that just from my sample, this average is a little bit bigger than these two averages, okay? And then a negative value is going to come out. Another way of understanding that is that if P and Q are the same, this is an unbiased estimate of a quantity whose expectation is 0, right? I've got a sample estimate of a quantity whose expectation is 0. That means that sometimes by chance I'll get numbers less than 0, sometimes by chance I'll get numbers bigger than 0, because I have, as I get the infinite sample limit, that the mean converges to 0. So I have to get below and above. I hope, Simon, that answers your question. Oh no, my video was unstable. Okay, let me answer that question again. Sorry about that. Let me know again as soon as possible if the video is unstable, and I'll repeat the answer. So basically, like I've taken the average. Okay, the question is, why can the MMD be negative? I've got this average here, I've got this average here, and I subtract this average here. Let's say P and Q are very close, or even the same. It can then happen by chance when I draw samples that these two values sum together are smaller than this value. That means that this negation is bigger than this sum. That means I get a negative MMD out. Okay, just by chance, I'm computing it from samples. Okay, so I am getting an MMD, which is an unbiased estimate of a quantity whose mean is 0 when P and Q are the same. That means that occasionally I'm going to get negative values, occasionally positive values. Does that answer your question, Simon? And was my video stable throughout? Okay, great, perfect. Yeah, please let me know as soon as possible if my video becomes unstable. Normally my internet's behaving itself. Okay. Now, we want to test threshold when P and Q are the same, right? Because we want a threshold that we exceed with low probability when P and Q are the same. Like that's going to tell us if it's likely that P and Q match or not, right? So we need to look at the typical behavior of MMD when P and Q are the same. So let's run the same experiment. Let's say that P and Q are the same, right? They're just, in this case, standard normal 1D, like as simple as a distribution as you could possibly think of, okay? Here, again, on the x-axis, I'm plotting MMD. On the y-axis, I'm plotting the number of times I've seen a particular value of MMD as I repeat my experiment. Notice, however, that I'm scaling this time by n. Now, statisticians in the audience should be worried about that. They should wonder what on earth is going on, that I'm scaling by n and not root n. So this is a good warning, but let's repeat the experiment. One other thing. Notice that I'm seeing negative values of MMD here. This is for the reason that I explained earlier, right? I'm computing empirical average of P to P, empirical average of Q to Q, minus twice empirical average of P to Q. Now, when P and Q are the same, sometimes just by chance, I will get that the first two sums are less than twice the final sum. And in this case, I'm going to get a negative MMD. That's fine, right? Because I want a quantity that on average is going to be 0, right? It's an unbiased estimate of a quantity whose mean is 0. Okay, so here I've got some MMDs I'm computing with this is standard normal here. Here I've done 10. Now I've done 20. Now I've done 50, 100, 1,000. This is a little worrying, right? It's not looking like a Gaussian. And indeed it's not, right? It turns out that when P and Q are the same, MMD converges to a distribution that's exceptionally unpleasant, right? It's an infinite weighted sum of centered chi-squareds, where the coefficients of this infinite sum are the eigenvalues of my kernel with respect to P. Now I'm saying this is an unpleasant distribution because in the great majority of cases, I can't even compute these eigenvalues. I don't know what P is. In the case where P and Q are standard normal, it so happens that I can compute them in closed form, but almost always I can't. Okay, so I know how MMD behaves typically when P and Q are the same. However, what I know is that I don't know because the distribution of MMD, like the way that MMD typically behaves when P and Q are the same, has this incredibly intractable form. And this is, a little bit frustrating. So just to summarize, when P and Q are different, MMD behaves like a Gaussian distribution generated around its mean. I'm scaling by n here, which is why my Gaussian is so flat. Okay, when P and Q are the same, I get this very weird looking distribution, which is centered around its mean, which is 0 here. Okay. Now this is a problem because remember my goal. My goal was to get a threshold which the MMD should exceed with low probability, with probability alpha, when P and Q are the same, right? So that's the threshold. Below that threshold, I conclude that P and Q are probably the same. Above that threshold, I conclude that P and Q are probably not the same, right? That's what I want to do. Like this is the threshold I want to construct, okay? So I want to control the number of false positives I make. Now, in the event that P and Q are different, this area here represents the number of false negatives. So these are the cases when P and Q are really different, but by chance, I was unlucky. I just so happened to get an MMD here, which is below my threshold. So ideally, I want not too many false negatives, and I want to control the number of false positives. But this is a problem because my C alpha is a quantile of a distribution that I just told you is horrible. So how on earth am I supposed to compute it? Okay. So it so happens that there's a numerical strategy for computing this threshold, which is consistent, which is giving a threshold which is correct for this setting. And this is using a permutation approach. And I'm going to show this approach here. Okay, let's say X are the distribution over dogs, Y are the distribution over fish. This is my MMD. On average, how similar are dogs to dogs? How similar are fish to fish? Minus twice how similar on average are dogs to fish. So obviously dogs are very similar to other dogs, fish are very similar to other fish, and dogs and fish are not so alike. Okay, now let's take my bag of dogs, my bag of fish, throw everything together, scramble them all, and draw half my samples from this bag and call them X tilde, half my samples from this bag, call them Y tilde. So these are permuted dogs and fish. So these are mer dogs. It's half a dog, half a fish. Okay. So here's my X tilde, scrambled bags of dogs and fish. Here's my Y tilde, a scrambled bag of dogs and fish. And now let's compute the MMD for these mer dogs, half dog, half fish. Okay. Now, with these scrambled bags, I'm getting the x tildes that are on average as similar to each other as x tilde is to y tilde. Now there's some noise, I'm computing this from samples, but basically this is a simulation of the case where P and Q have the same distribution. Okay, so which in this case is a mixture of dogs and fish. Now, if I do this many, many times, okay, in the event that P and Q are the same, if I take the quantile of this simulated distribution, I will get the threshold. I will get a consistent estimate of this threshold, okay? In the event that P and Q are different, I will get a consistent estimate of the threshold for mer dogs, but because dogs and fish are different, as I see more samples, false negatives are going to go down to 0 for this threshold. So basically, if P and Q are the same, I'll get the right threshold, I'll get the right rate of false positives. If P and Q are different, I'll get false negatives going to 0. So in both cases, I win using this permutation trick. Is the permutation trick clear to everybody before I go on? Yep. Okay, very good. Okay, so now we get to the sort of finale for this section, which comes back to one of the earliest questions and a very good question that I got early on, which is how do you choose your kernel, right? So ultimately, I want to choose a kernel that best distinguishes P from Q. Now I've said right at the start that if I use a characteristic kernel, MMD in population with infinitely many samples is going to be 0 only when P and Q agree. So that's great. But the bad news is I don't have infinitely many samples. I have finitely many samples. And for finitely many samples, some kernels are better than others. Okay? And in particular, for finitely many samples, I might be in a situation where I get, for let's say, 1 million samples, I've chosen a kernel which is characteristic but not good for my problem. I still might not be able to distinguish P from Q. Okay? I just got the question, what happens if there's a different number of samples from P to Q? You can still define the test then. However, if you want your probability of false negatives to go to 0 as the number of samples goes to infinity, you need the number of samples from P and Q to go to infinity, even though it might be that there's an unbalance, okay? So even though there may be more samples from P to Q, I need the number of samples from P and from Q to go to infinity if I want the number of false negatives to go to 0 as I see more samples, to answer that question. But yes, you can define all of these things for unbalanced samples. I just didn't do that because it's more notation. Okay. So then the question becomes, how do I choose a kernel which is the best in my class of kernels for the problem that I'm trying to solve? Okay. There is no one kernel that solves every problem, right? There's no like super kernel that solves everybody, right? So for the samples that I've seen, I want to choose the best kernel. And I have a strategy to do that, okay? So there is a mechanism for doing that. Okay, so let's first of all illustrate good and bad kernels for a simple 1D example, okay? Here's my exponentiated quadratic kernel. So it's this e to the 1 on 2 sigma x minus y. Now, we know it's characteristic. We know that in the infinite sample limit, the MMD computed with this kernel will only be 0 when P and Q agree. So we know that as the number of samples goes to infinity, the number of false negatives has to go to 0, right? But the choice of bandwidth is very important for finite n. So here is a good bandwidth for finite n, okay? Here is my witness function. So could I give a concrete example of K where the case at x are pitches? I'm coming to that. I'm going to show you exactly that very shortly, okay? But let's start with this 1D example, okay? Here is my kernel, 1D Gaussian. Here is my P, here is my Q. This is a sensible kernel for this problem because here is my witness function, and I can see that EP, expectation under blue of my witness function, minus expectation under red of my witness function, is going to be large. Okay, so I'm very good at distinguishing P from Q in this case. Here I've chosen to broader kernel. Okay, So this is a very broad kernel. My witness function is very smooth. Now here, EP of f minus EQ of f is very small, right? And so this is not going to be great at distinguishing P from Q. So when I've chosen too broad a kernel, like obviously when I've got infinitely many samples, I'll be able to see it. But for finitely many samples, I'm not going to be able to see it because I've chosen too broad a kernel. Now here's a subtle one. What if I've chosen too narrow a kernel? Well, it seems this narrow kernel is a really great choice, right? Because EP of f minus EQ of f is large here. Great, I win. I've found a big difference between P and Q. The issue with choosing too narrow a kernel is wherever I put my red points and wherever I put my blue points, I'm still going to find a large MMD. So MMD is going to be large whatever I do. And that means that I won't be able to distinguish a true signal from a whole bunch of false positives, right? So a whole bunch of like junk signals. So basically, if MMD is always big, that's not helpful because then it's not bigger for this case than for the case when P and Q are the same. So a narrow kernel is no use to me either. So too narrow, too broad, just right. And I want to somehow get in this just right scenario. Okay, and coming back to images, I'm not going to use this kernel on images. Like that's a silly idea. Okay, so I'm going to need to have a kernel on images that is much more sophisticated, that is using features that are going to be informative about images. Okay, so how do I choose my kernel? Ultimately, I control the rate of false positives, right? I've told you how to do that using this permutation trick. And so a good kernel would, for a given false positive rate, minimize the number of false negatives. So my just right kernel is going to have a very small area here for a given number of false positives. So, how to choose the best kernel seems to have quite an easy answer. I just minimize this area. But this area is hard to compute. In particular, it's the area below this quantile that I've computed by permutation. And this quantile is also going to change as I change my kernel. So that seems to be a hard optimization problem. But it turns out that we can take a shortcut, an approximation, that is actually pretty good in practice. Okay, so this is the power of our test. So this is the probability that we're not in this bad area here, but we're on this side here. Okay, probability under the alternative, P not equal to Q, that n times MMD exceeds the test threshold. Now, lucky for us, when P and Q are different, this has a very simple form, because when P and Q are different, MMD is Gaussian distributed. So the expression for this is given by the CDF of the Gaussian, evaluated at the MMD divided by the variance under the alternative, minus C alpha divided by n times variance. Now this n here arises because I've multiplied by n here. Okay, so this is the probability of getting a true positive. Now, I would ideally want to maximize the argument of this, right? CDF is monotonically increasing. If I maximize the interior of this argument, I would maximize my chance of getting two positives. And that's great, okay? But the trouble is that C here is a function of my kernel. So if I'm maximizing the argument of my CDF, I would need to determine how C alpha is changing as I modify my kernel. And that's hard. Here's the shortcut. I know that, by the central limit theorem, my variance as I see more samples is dropping as 1 on n, right? As I see more samples, my MMD is concentrating down onto its mean. So square root of Vn goes as n to the minus half. 1 divided by square root of Vn increases as n to the plus half. This quantity here, though, because I've got this factor n here, n times something that drops as n to the minus half, when I take the reciprocal, this decreases. So I've got one term that's growing as I see more samples, one term that's shrinking as I see more samples. And when I have a reasonable number of samples, the first term dominates the second. And lucky for us, we can compute every term in this expression in closed form. So I've already shown you how to compute the MMD. The variance also has a simple expression, which I'm not going to show here, but you can compute it in closed form. So that's great. So what that means is to an approximation, if I want to minimize the number of false negatives, maximize my power, all I need to do is to maximize the signal to noise, the ratio of the statistic to the square root of its variance. What does that mean graphically, right? Let's go back to our graph. I want to push the mean of this blue curve to the right, and I want to make that blue curve as narrow as I can. And if I do that, I make this area small. So that is, to a good approximation, a great way of minimizing the number of false negatives. So if I optimize my kernel to maximize signal to noise, MMD on its standard deviation, I'm going to get a good kernel out. And that will put me in this, this just right scenario here, we hope. Okay. So one subtlety, and this is extremely important, is that we can't train our kernel on the data that we test on. Okay, if we train our kernel on the data that we test on, we are going to get an elevated number of false positives. This is a form of overfitting. So if we are going to adapt our kernel, we need to leave aside some of our data to train our kernel and then test on the other half. So this is a graphical illustration of this. Let's say that this table here represents our P samples. Let's say that this table here represents our Q samples. Now I'm going to take the red half of this table, and I'm going to use that to choose my kernel. Red half of table P, red half of table Q. I'm going to choose my kernel by maximizing my signal to noise. I'm going to take that kernel, and then I'm going to use that kernel on the held out data, on the test data, to do my test. If I do that, I will not damage my test. I'm not going to get an elevated rate of false positives for my test. So this is actually what we do in our paper. This is very important. If you don't do that, you're going to get junk. Okay, so make sure you do that. Now, coming to the question that I got earlier, what happens if I want to define kernels on images? Like I'm sort of going back to the problem that I started with, which is that I want to distinguish CFAR10 and CFAR10.1. Okay, now to do that, I need to use a much more sophisticated kernel than just an exponentiated quadratic. In particular, I want to use kernels on convolutional neural nets on my data. So kernels on features on data. Now, in the paper that we published, this is the sort of complicated hybrid kernel that we defined. For more details on why we chose that kernel, I'm going to refer you to the paper because we're running out of time. But what this is an exponentiated quadratic defined on a neural net on our data, plus an offset multiplied by an exponentiated quadratic. Okay, so in particular, this kernel is adaptive. I'm going to learn these features by maximizing signal to noise on a training set and then do my test on a test set. Now I'm going to next describe what's going on in this plot. So this plot is actually a little bit complicated. So it's going to take a little bit of explanation. For this plot, I'm using this hybrid kernel, but rather than using complicated conv nets here, I'm just using like pretty shallow, fully connected nets. The problem that I'm trying to solve here is doing a two-sample test where I'm trying to distinguish the red samples from the blue samples. Now, in this case, my red and blue sample distribution is this distribution of a grid of blobs. But the difference between red and blue changes depending on which blob that I'm in. Okay, so for this blob here, I'm seeing more blue up here and down here than I am, and I'm sort of seeing that the red is sort of skewed to the right. Okay, here blue is isotropic. So blue is just a spherical Gaussian. Red here is a Gaussian skewed to the right. Here, blue is isotropic. Red is a Gaussian skewed to the left. So basically, in this case, blue has more mass here, and red has more mass on that sort of skewed line here. Here, blue has more mass here, and red has more mass skewed on the line. So now I hope that the difference between blue and red is clear. Okay, in the middle here, blue and red are exactly the same. Okay, and then down here again, we've got red is skewed to the right. Here, red is skewed to the left. Okay, so what this means is that the ideal kernel to distinguish red from blue is changing as I move around from my space. Okay, now the final part of this plot are these contours here. These contours here are actually the isolines of my kernel evaluated at the center here. Okay, so these are, if my kernel is Gaussian, or if my kernel were Gaussian, these would be perfectly spherical. But because it's Gaussian evaluated on neural nets of my data, I actually have a funny squishy shape here. And this squishy shape is optimal for locally distinguishing red from blue. But then my kernel changes shape over here. So here my kernel takes a different shape. And that shape is optimal for distinguishing red from blue on this part of the space. So my kernel is no longer the same kernel over my whole space. My kernel is adapting. My kernel is adaptively changing shape over my space so that it's best at each region of my space for distinguishing red from blue. And I do that by using this kernel trained on, in this case, fully connected shallow nets, I think 3-layer here on my data. So this is the power of using kernels defined on neural nets, is that I now have an adaptive kernel that is much more powerful because it's sort of changing depending on where I am in my space. Okay, so a sort of philosophical point given here by Hippolyte is that we can sort of think about the alternative distribution, which is normal. This would be great. The trouble is that, like, by definition of statistical testing, our interest is in the case that P and Q are the same, right? I'm saying that, like, I want to reject the null hypothesis that P and Q are the same. So ultimately, like, the default is that P and Q are the same, and the let's say hypothesis that we're making is like, what if that's unlikely given our data? So that's sort of classical hypothesis testing. If our default were that P were not Q, this becomes very hard to characterize because, like, P and Q can be the same in only one way, but P and Q can be different in a multitude of ways. What if they're different but super close, right? So it's very hard to sort of characterize a hypothesis test when our starting point is P and Q are different, because P and Q can be different in too many ways. So that becomes a little challenging. One could somehow argue, and this is sort of drifting a little bit, that P and Q could be sufficiently far different that I know that that difference is bigger than some amount. And that's an interesting question, but that's a question I'll leave for another time. Okay, so returning to the slides, here I've got a very complicated P and Q, which differ in different ways in different parts of the space. And I've defined an adaptive kernel, which I've learned by maximizing signal to noise, which is changing shape across my space. It's changing shape because of these neural nets. And it's changing shape in a really, I think, a really helpful way, which is adaptive to the local differences in P and Q. Okay, so this is to demonstrate just in 2 dimensions that it is possible to learn kernels on neural nets on data, and these kernels on neural nets on data are very helpful. They're going to give you much more powerful tests than just a Gaussian kernel everywhere. All right. Now let's go to this nice example that I started the lecture with, which is CIFAR 10 versus CIFAR 10.1. In this case, we again use this kernel, but now rather than using not too deep fully connected nets, we're using quite deep conv nets. But we're again maximizing these conv nets by maximizing the signal to noise on a held out set. Now, I think very interestingly, even though it's very hard to distinguish CIFAR 10 and CIFAR 10.1, so humans are not able to make that distinction, our test is able to tell that P and Q are different, right? That CIFAR 10.1 is indeed a different distribution to CIFAR 10. And what's interesting is that Ben Recht has shown in his paper that a classifier trained on CIFAR 10 and tested on CIFAR 10.1 is going to make more errors than it would on CIFAR 10. So even though in CIFAR 10.1, the authors made every effort to make these distributions as similar as possible, nonetheless, there remains a difference, and we're able to find it. So, in answer to the question, what is a kernel one would use on images? This is the kernel you'd use on images, but keep in mind that you need to train these features on a held out data set for us to be able to apply this kernel. But if you do, then you can solve actually a very challenging problem. So this paper was published in ICML last year, and the code's online. So again, like if you want to use this, if you've got some complicated data that you want to do a 2-sample test on, you can download the code and you can try it for yourself. So this is all made available, and we're happy to help out. All right. So I think that concludes the talk. So I'm going to end with some kernel beer, which is a great beer you can buy in London. And I'm happy to take some further questions. If there are further questions. I mean, one thing we could come back to, there was this earlier question on community detection. I wasn't sure that I quite understood that question. So if I mean, it's gone up in the chat a bit, so I can't find it anymore. Okay. Oh, here's an interesting question. How suitable is this for out of distribution detection? So this is an interesting question, right? The question might be like outlier detection. So in this case, I would have a sample from P, like with, let's say 1,000 samples, but I just have a single sample from Q. In this case, I would not use MMD. I don't think that's a good idea. The reason is because the guarantees that you get from MMD apply when the number of samples from P and the number of samples from Q go to infinity, right? This is not the case when you're looking for out of distribution, like a single sample, like if you're trying to find if a sample is an outlier or not. For this, you should use specialized methods designed for outlier detections. So there's a number of methods in the literature for that. MMD is for sure not one of them. Okay, right. So this is a question I'll return to. So let's go back to MMD. Okay. So the question is like, why can MMD be negative? Okay, MMD is indeed a norm, right? MMD squared, in fact, which I'm using, is the squared norm of the difference of expected features under P and Q. Okay, so this population quantity is always greater than or equal to 0. And when P and Q are equal, it's exactly equal to 0, right? Now, let's go to this final line. This final line is the average similarity of 2 independent samples from P, average similarity of 2 independent samples from Q, minus twice average similarity of samples from P and Q. Okay, so this is once I've expanded this out into a sum of terms that I can compute, which are terms with kernels. Now let's compute these from samples. Okay, that's the next slide here. Okay, what's on average the similarity of P and P? Okay, this is the average sum of kernels between dog I and dog J, excluding the diagonal terms, right? Okay, so I've got samples of dog and dog, sample and fish, average sample of dog and fish, right? Now, this quantity here is an unbiased estimate of this quantity here. That means if I take the expectation of this term, it's going to be equal to this term, right? This is the average kernel between X and an independent sample drawn from X. All right. Now, if I have an unbiased estimate, okay, so if I take the expectation of this, I would get E of K of dog and independent dog, right? Because my samples are IID. Okay, so indeed it's unbiased. If I had these collider terms, I'd be in trouble because I'd have the average similarity of a dog on itself, and that's a problem because I'm saying that in population I want dog and independent dog. Okay, now let's say that P and Q are the same. That means that in population, MMD is 0. That means that if I have an unbiased estimate of this, I'm going to get a scattering of points, both above 0 and below 0, because I need that on average, the mean of this scattering of points is exactly 0. You can see this if you look at this histogram here, right? You can see that, on average, the sample is going to be mean 0, but I've got some points above, I've got some points below, and if I average all of these up, the expectation is going to be 0. So, this, in this sense, it shouldn't be a surprise because, like, I'm computing from samples a quantity that I know in the infinite sample limit is going to have a mean of 0, and it's unbiased, which means that if I take the expectation of all of these experiments, I'm going to hit a 0 mean. Looking at the expression, you can see even just intuitively why this is. So let's think of the case where I have X, which are dogs, and Y, which are also dogs, okay? I've got a bag of dogs, I've got another bag of dogs. Now, I'm computing the average similarity within my bag, but these are all dogs, okay? Now, when I take the average similarity of dogs from one bag and a dog from my other bag, there is no reason why these two sums should be larger than this sum, right? It's all dog-to-dog similarity. So it can happen by chance that twice this sum is bigger than this plus this, right? It's all samples from the same distribution. And so this is why in practice you can expect to see some negative numbers when you compute this. As I see more samples, it's going to converge right down to 0. So I hope that answers. I wanted to make that clear, which is why I gave the long explanation, but I hope that makes it clear. Okay, let's look at some other samples. Okay, but I hope Tom and Marnix, this answers your question. This answers your question. Okay. Now, will the kernel lead to overfitting? This is a very good question. Now, if I trained on the data that I tested, then absolutely yes. But I don't, right? I don't train on the data that I tested. I train my kernel on one sample with my signal to noise, and then I test on another sample. That means that the worst that could happen is I learn a kernel that is somehow like, let's say too powerful, too specific to my training sample. If this happens, then I'll just basically never notice a difference in P and Q on my test sample. The reason is that like whatever P and Q are, I will always get like, some random number. So whether P and Q are different, whether P and Q are the same, I'm just going to get a number which is indistinguishable from the case when P and Q have no difference. Now, it so happens in our experiments that when we maximize signal to noise, we don't get this scenario. So we basically get a kernel where we've learned it on the training data, we've deployed it on the test data, and we're getting the right number of true positives while still controlling the number of false positives. So we're not overfitting. The number of false positives is still at the design level of 5%. So, with the kernel that we've done, using the training procedure that we've described, we're not getting overfitting. But, if you were to train on your test data, yes, you would overfit. In some scenarios, you might overfit in such a way that you never detect differences. But this is not what happened in our example. Can you use MMD to create similar training and validation sets? So MMD has been used actually in covariate shift in a very early paper. So the answer is yes. So in fact, in Europe's 2006, we proposed that, and we made a longer version of it, I think, in 2008. So the answer is yes. Yeah. Okay. Okay, so can MMD expand to multi-label comparison? So I'm going to give like a quick answer to that, right? So let's say that I have, rather than 2 samples, P and Q, I have 3 samples, P, Q, and R. Okay. Now, what kind of question might be interesting in this case? Well, here's an example. Okay, let's say R is my reference sample. Okay, R is my real bedrooms. And I have 2 different GANs. Let's say I've got a GAN that I trained with Wasserstein, a GAN that I trained with KL. And I want to know which of these 2 GANs is closer to my reference. Then this could be interesting, right? I would say, is P closer to R? Is MMD from P to R smaller than MMD from Q to R? So this is a reasonable question to ask. And this is actually a question that we've answered in a couple of papers. So on my page, you can see papers of like, let's say multi-way comparison between samples. And this is used exactly in the setting that I've described, when we've got multiple candidate models and we're seeing which of these candidates is closer to the target. So the answer is yes. And this is an example of such a case. Any other questions? No more questions. Great. All right. Well, thank you for your patience and for many excellent questions. I think that's been very enjoyable. I've really enjoyed how interactive this has been, and I've also got some great references to follow up on. So thank you once again for inviting me. It's been very fun.
Okay, Arthur, thank you for your great lecture. You can see all the responses from the students, and I think we're closing. Yeah.
Great. Well, thank you very much, and
okay.
I wish all the students a fantastic summer school.
Yeah. Okay. Have a nice day.
Thank you. Bye.
Bye.